Wir sind im Zoom-Meeting noch nicht gespotlightet.
Good morning, good afternoon, and good evening to all our participants of Android Security Symposium 2020 again for starting our second day. The first day yesterday, we believe, went very well. There were some minor technical glitches, but otherwise all the major aspects worked beautifully. And we saw the results. In terms of numbers, this was not only the most diverse Android Security Symposium so far in terms of participants from different countries, as we were able to show you yesterday, but it was also our most active Android Security Symposium to this date. We had 200 to 250 concurrent live participants at different given times. We had over 1,000 views of the YouTube stream at the time of closing and nearly 2,000 before our start right now. Over 600 cumulative hours of watch time were already happened yesterday on the YouTube stream. And what was positively surprising to us and is an indication that virtual events can actually work nearly as well as physical ones, is that we had nearly as much, or I think comparable, interactivity to our last two instances of the Android Security Symposium as well, with over 56 total minutes of just Q&A time, which was nearly a quarter of the whole active presentation time yesterday.
Yeah, as we already mentioned yesterday, and we can't mention that often enough, thank you very much to all of the speakers. All of the speakers do their presentations for free. They donate their time to this event to give you, the audience, very impressive, very interesting talks and insight into their work, into the interesting work topics. And yes, we would really like to thank you all for doing this. Yeah, the program for today, we will immediately after our introduction start with session 1. Today's host for the session 1 is William Enck. Do you want to say something?
William has been part of Android security community for a long time, and we're happy that he agreed on quite short notice because we had another cancellation. So William, thanks a lot to you for stepping in just yesterday and agreeing to chair our first session, which is 2 talks on some very specific but highly interesting topics of where Android is actually going, leading over to our sessions 2 and 3.
Yeah, after about an hour of break or 50 minutes of break, we will start into the last 2 sessions of the Android Security Symposium, the 2 keynote talks by Alex Gantman and Sudi Hörle. Yeah.
For closing our Android Security Symposium today, we will only have a few more words at the end, but no specific ceremonies. We'll just close off with, again, reminding people to watch and share the YouTube link and use maybe the interactivity that is still ongoing. Please use the self-introduction channel at our virtual conference venue, the Mattermost chat, to introduce yourself at this day if you haven't done so yesterday, and to contact each other if you have common topics. And use those networks, use those contacts that you found yesterday or that you will find today in the next month, in the next year, to work together on improving the security and privacy posture of the Android ecosystem. Thank you so much.
Yeah, and with this, we would like to hand over to Will to start into the first session.
Great. Thank you, Renee and Michael. So if you closed out with us yesterday, we ended on the topic of privacy, and that's where we're going to be picking up today. And so we have an excellent talk from Dinesh Venkatasan and Aditi Bagnikar, who are coming to us from Microsoft at Hyderabad. So I believe that Aditi is going to be kicking us off with this. Are you there, ready to get set up?
Hello.
Hello.
Yeah, hi. I think we can begin with.
All right. So would you like to share your screen?
Yeah, sure. Just in a minute. So let me know once it's visible.
It's visible. Take it away.
All right, and let me stop my video. All right. So thank you, first of all, the organizers for giving us this opportunity to present the work. And hello, everyone who is watching this right now. So today we will be talking about the privacy posture of apps ecosystem, particularly Android. And before jumping into the technical details of it, let's first introduce ourselves. I am Aditi. I'm an engineer and researcher. My major interests are in technosociology and passionate about studying all the different aspects in which tech shapes human life. I'm a digital well-being advocate and an avid blogger. And with us, we have Dinesh.
Hi all. I'm Dinesh. I am a malware researcher and I have been studying about various security threats for the best part of the last 2 decades. And I like knowledge graphs, and I am in a lifelong pursuit of building a knowledge graph of all security threats. I am very much interested in building intelligence system that has the ability to do causal inference, and we will talk more about that in our case studies. Over to you, Aditi.
Sure, and thanks, Dinesh. Just beginning with the disclaimer that all the opinions are our own and does not necessarily reflect that of our employers. So let's talk about the functional perspective of privacy today, like understanding the context as to what privacy stands for in the real life. And as we go in the presentation, we will try to map it in the digital world and talk about the posture there. So privacy is a very basic human instinct, right? All of us live in our homes. We have houses surrounded by walls. We control the doors for letting people in and out. In real world, if someone asks us a question like what's your exact address or phone number, we get suspicious for sure. And most of us, like some of us, put locks on main gates for security purposes. So it's like a very basic gesture that human beings relate to. And it's very contextual, like privacy for me might not be privacy for you. So definition is really abstract. And I think that is what makes it really challenging to map this humanly expectation into a digital sphere. But still there are common themes attached to this, which we can all relate to. And that's what we'll talk about. First thing is autonomy. So why privacy? What is privacy protecting? So if you think about it from a perspective of technosociology, we'll say that it's giving, in a way, it's protecting our autonomy. Like how do we function, controlling our own lives, having the full freedom of how we choose to live our lives without the judgment or suspicion of any other person whom we don't know or people who have access to our information. So it demarcates that personal sphere from what we want people to know about us. And when is your privacy actually at risk? So imagine that my neighbor invented this elaborate X-ray device that enabled the person to look through the walls. Now, I would say that the person has the control to look at what I am doing, but that essentially doesn't, put my privacy at risk until that particular act is performed. So even if all OS, Android, or different operating systems have access to a lot of information, until that act is done, it is not affecting the privacy. And secondly, the most important thing is that who gets to see and what is it that they intend to do with information that they acquired. So will it affect your autonomy if anyone is taking details from your devices? I would say it would affect it if it is affecting how you live your real life, right? So examples of it would be like if someone is taking details from my device and then presenting me information which can possibly manipulate my thought process, then yes, it is affecting my privacy. Another thing would be like, suppose some app sitting on my device collects some information and it's passed on to some servers, which is deciding whether I'll get a loan or not. So there's data flowing out of my device, and that data is being used for my credibility or my judgment of whether I should be given a loan or not, then yes, it will be affecting the privacy. And similarly, it goes with surveillance. So if we know that, okay, someone is watching through the webcams all the time, the way people will behave will be restricted, and that will definitely affect the way you live, right? So this is how, if you do a technical mapping, privacy will get affected if things are leaked from a system which we don't want to. So now mapping it into the digital spheres, let's talk about what happens in Android world. From technical standpoint of privacy, platforms usually try to ensure two things. First is that the users have all the control to provide or revoke consent on sharing data. So they should have the control. In Android, usually it comes in the form of permissions. And second is that the platforms itself is secure. So you ensure that the data reaches only to the legitimate consumers and is handled with proper care. So let's talk about the first and then deep dive into the second. So if you have an Android phone, what is it that you can control? So typically, a user on an Android phone can control, first of all, the apps that get to live on the device. Now, this is under our control most of the times, apart from the cases where the app is a system app, so it's coming with your phone, or if the app is mandatory by the law of land. In those cases, you don't have control, but other than that, you always have the right to decide what app is installed. Then the permission that that app can take, that can also be regulated by the user. And the configuration changes that the app can make. So suppose turning on the accessibility service or device admins, those things can be controlled by going to settings and then deciding the controls for that particular feature. But now let's talk about what a user cannot control. So most of the users, Android users, have this thing that if I'm giving a permission, then I know, okay, this is going out of my device, but what is the real scenario? So info can go out even without any permission. And here's a small Jon Snow app that we made. So this particular app has not even a single permission, not even the normal permissions that Android can take without user intervention. Android app can take without user intervention, but let's see what all this app can get from the device. So here is a Jon Snow app, which we think knows nothing. And there's no permission given to this app and no other explicit settings. Now, when I go to the app and ask, what do you know? Now it'll tell me you have the Google Pixel 3 basic device details, the ABIs, the bootloader, all the digital details, which is, I think, okay, fine if they know. Then they would know whether ADB is enabled or not, or USB mass storage is enabled, or whether my Wi-Fi is on or not. They'll know what kind of accessibility services I'm using. What are my preferences? Is there any parental control on my device? They would also know all the apps which are sitting on my device. Now, essentially every app that I use has a trait associated to it. If I'm using HDFC Bank app, it means that, okay, I don't use that, but if I use that app, it means that this is my bank account, right? Most of the cases. Similarly, if you use any other app, basically it is a characteristic trait which can be used, and any app on Android can get access to that, all the different apps which are sitting on your platform. Then we ask, is there anything more that you can know? So this is the question we ask next, and let's see what is the answer. So further, the app can tell when will my alarm trigger next? When will I wake up next according to alarm? Am I listening to a song right now? Is my microphone on mute? Is my battery charging? What is the last text that I copied? Which is, according to me, an important information. If you use copy paste in mails or chats, this app will be having access to it. Then the sensors and all the app widgets that I'm using. So this is information that this app, which practically has no permissions, can get from the system. And I'm very sure there's a lot more to it. It's the first trial of conducting this experiment. And the normal permissions are all these permissions that you can see on a screen are normal permissions, which mean that user doesn't have to give consent on these permissions, but still this data can be accessed from the device. And this is like a lot more comprehensive than what we have just seen. So including the Wi-Fi network, the MAC addresses and everything, which we can get using these permissions. So things that this can conveniently lead to is firstly user profiling, as we see that, as we just saw, that in apps, every app is a trade. So if an app is able to collect all these things, the app would definitely know about my digital habits, how often do I open my phone and different things like that. And all that can definitely lead to user profiling. In fact, there has been significant research, which you can see quoted on the PowerPoint, where they were able to clearly find out the gender of the person, ethnicity of the person, and different things related to that person. So personal traits of the person can be figured out just on the basis of this information. And the second thing it can lead to is device fingerprinting, which is a notion very common in web, where we try to fingerprint the browsers. But in Android, that surface just increases. So it's a lot of data points on which you can easily figure out that this device is unique. Now let's shift the focus a little bit on the alternate angle of looking at privacy. So when you give access to it, is it that you're just permitting access for your data? So humans are interconnected, and so is our data. There's no isolated zones in data. So when you give access to your contacts or location or different things that you choose to share, that same information includes your family or friends' contacts and photos as well. So that also goes away. Similarly, when I choose to share my location or Wi-Fi state, my flatmate's location and Wi-Fi state also goes away. So it's kind of interlinked. So similarly, so the problems that privacy and security researchers usually see in this domain is this curious case of crowdsourcing, where say we have Alice and we have Bob, and Alice shares her number with Bob, and then Bob installs some app which takes that number and put it on cloud. Alice gets to know about that information, that it's on the cloud, and she gets disappointed that it's on the cloud. So she raises a request that, hey, just take this information away from the cloud because this is my personal PII, this is my personal information. But again, if third person comes here, Carol, and Bob shares the contact with Carol. Now Carol chooses to upload the information. They don't exactly choose, but suppose they have some app that took the permission and shared it on the cloud. Again, that would lead to the same problem, and Alice will be disappointed that her data is on the cloud. So basically it's a thought-provoking question on how do we approach such kind of problems, because there's no clear, well-defined solution on how do you want to tackle this kind of situation. Can a person actually control what amount of his or her information is on the cloud? So that is getting challenging. The other question that we touched upon was like, who gets to look at the data? Now, I'm not saying that we just should not share any data. That's not possible. If I want to use map apps, obviously I have to share my location because the utility will be provided using the location. So apps that need context to perform, legitimate apps which handle the data with care, definitely we share and we assume it's secure because we trust into the system and the owner of the app, the people who build the app. Second thing is the ad libraries which are into legitimate apps. So because of the freemium version of model of revenue in Android, the apps will give you services, but it won't ask you to pay. So they use ad services and we trust those services. So in both first and second case, the things will go wrong until and unless the data is not handled rightly. There have been significant policy changes and introductions to make sure that data passed to these are handled with care. But things like programmatic bugs in your program, putting information in logs or handling the data wrongly, or if the data servers themselves are in attack, then definitely we lose out our privacy in those two cases. But the third one is what we are interested in and what we will be more covering in the technical details in coming slides, which is adware embedded in POA and PHA. So the first two are like they try to use the right ways of getting the information, but the POAs or PHAs that we study, they cross the margin and try to get access to data which they don't have the permission to access through indirect ways or shady ways, as to say them. And then fourth thing comes surveillance, where they can also get to see, which is a combination of privacy and security threats, but it's an ongoing discussion and out of scope for this presentation. So yeah, so this is kind of covering the different kind of privacy threats that we just discussed, a little bit more details on them. And with having that context of privacy and its mapping with digital sphere, let's switch into the technical perspective of the presentation, where we'll be talking about the vulnerabilities exploited in privacy threats. So over to Dinesh.
Sure. Thanks, Aditi. Could you please move to the next slide?
Sure.
Yeah. So in this section, we will talk about some of the previously unknown tricks which were deployed in PUAs and PHAs and some of the cases were POCs. So we will first begin with an exploitation of a boundary condition check and how it helps a PUA to attain a certain privilege which otherwise would not have been possible. Before diving deep into the concept, let's talk about some of the background details. In Android, if an application wants to draw a window that has to appear on top of every single app, it has to acquire a special permission called system alert window. And all the system windows have certain numbers associated with it. If it is an error window, there is a number 2003. If it is a phone type window, there is a number. And what happens here is in the implementation, there was a flaw. The lower bounds condition was not being checked in the implementation. Hence, some of the PUAs in the past have utilized that unknown vulnerability. And they have set the value, passed the window type value as 0, so that the system draws it as a system alert window value. So using this vulnerability, the PUAs were able to draw a system alert window without having the necessity to get the system alert window permission from the users. This was already fixed, and let's see a demo in action. Aditi, could you please move to the next slide? Yeah. So as you could see here, so the device has two applications. One to show how the permission will generally look. So this is a harmless app. So it will require draw over other apps. That's the explicit permission it will ask from the user if it has to draw over other apps. But now we see an app which uses this exploit. So you could see there is no permission requested from the user, but still it will have the ability to draw a system alert window. So now this is a system alert window where it will appear on top of everything else. So the user will not be able to use the device as long as the other coercion happens in the background. Please move to the next slide. Another unknown trick is some of the PUAs, they were creating a user experience issue by creating a flood of permission requests. So again, before talking deep into the details, let's talk about the background of this functionality. From Android 6.0 onwards, a new dynamic permission model was introduced in Android so that all the apps will no longer get the permissions during the installation time. Instead, the permissions will be sought from the user as the app runs. So the condition for this dynamic permission model to be active in the devices, the apps has to target at least 23 and above API level. So when an app tries to access the dynamic permission model, it will pop up a window giving a rationale for the reason why the permission is required from the user. And this pop-up is done by the system level APIs. So there was an implementation bug in the way the permission request is transmitted to the user. So using that, an app can trigger a flood of permission requests, which floods the screen of the device. And eventually the user ends up clicking on the allow button. So yeah, we'll see the demo here. So as you could see, there is a flood of requests. Instead of showing two requests, the PUA keeps coming up with the new dynamic permission request flood. Irrespective of whether the user clicks allow or deny, as long as it is allowed and the next action is performed, it will continue to pop up even if you close the app. Next slide, please. Again, this issue was also fixed, and this is how the fix has actually happened. And the fix was implemented with the introduction of a private Boolean flag, yum has current permission request. And as long as this flag is set, the system will understand that already there is a permission request going on. So there is no point in allowing another pop-up to happen. However, this this hurdle was also circumvented by the PUAs and PHAs. We will talk more about it in the next slide with some background information. So this trick is not entirely unknown. However, the actual exploit is not unknown or documented. So the root of the problem is with the reflection. Long time ago, when we were young in the industry, we just noticed this behavior that we can use reflection to access private data structures of the programming language. So being curious, we reached out to a forum and asked, is it not a violation? And of course, it was working by design by then, but we kept tracking this and how it evolves. Next slide, please. So in JDK 9, eventually, after 10 years, the access to the reflection is now made as an warning behavior. Like if we run the program with accessing internal data structures of SDK APIs, it will throw you a warning, and in future releases, it will get removed. Next slide, please. So this shows when the same program is executed using the recent JDK, you could see the warning, and when it is executed using the older JDK, it simply runs well. Now, how does it relate to us and the topic being discussed? So from Android 9 onwards, the same behavior is implemented where certain APIs, internal variables, methods were prohibited from being accessed or modified via reflection. We will talk about the circumvention now. So now what has happened, the M has current permission flag is accessed via reflection and manipulated so that even though the flag is already set, the flag is reset to false so that the permission flood is triggered again. We will see that in action now. So this is a Android device running 8.1, and it is having that fix already baked into the platform. However, using reflection, the flag is altered, and hence the permission flood happens in the fixed version as well. Again, this is also now fixed. It is no longer a threat, but some of the devices, older devices, which doesn't receive the update, will continue to get facing this issue. So with that, I will hand over to Aditi to talk about the rest of the vulnerabilities.
Yeah, thanks, Dinesh. Talking about the next one, which is exploiting broadcast receivers leak. Now, most of us would be familiar with safe mode, right? Like whenever there is some unusual activity on my phone, I'll go to the IT admin and say, what's happening? The person would say, reboot it in the safe mode. And we expect that malicious code won't execute anymore because safe mode has to be implemented in that way. But there was a vulnerability in the device admin receiver in Android. So apparently, in the PHA, the potentially harmful application, registers itself as a device admin for the app. And even when the mobile is rebooted in the safe mode, when we try to deactivate that device admin, a callback goes to that app and gives an opportunity or window to execute malicious code. So let's see how it happens. So here I'm rebooting the phone in safe mode. I already have the app installed, which is a potentially harmful app, which is causing trouble on the device. So you can see it's in the safe mode on the left lower bottom. Okay, so I go to the settings and I try to take the device, this particular app, out of the device admin configuration. Now, when I click on deactivate, the ideal behavior is just deactivate the app and don't give the control to the app. But here in this case, the control goes to the app, and again, it's able to pop up the window. So this is pretty naive, not doing anything, but in the actual case, the adversaries were able to do malicious things in that window of opportunity. This bug is again fixed in the latest versions of Android, and we don't see it anymore. Then there was another very interesting trick, which was exploiting the string. So the apps have the Android label thing, right, which decides the name. So this vulnerability basically made that value of the label too huge that the package manager, the package installer, which maintains the installation and uninstallation of app, throw an error, and we are unable to remove the app from the device. So here's a demo for that. So on the right, you can see the long string, which we set as a label name. And on the left, we are trying to uninstall the app. And we see that we get a warning, it's not uninstalled. So this is the prompt from the installer, and then it has a stopped because the issue occurred because of the huge text string of the label of the app. So such kind of things are being exploited. This is also fixed, but these things have been exploited, and this is how they try to get to stay on the system, doing things that they want to, which is definitely in contrast to what we would want to on the system. So those are about the vulnerabilities. Now let's jump to a different section, which is client-side collusion, which is like a really active topic of research. We have had great talks on this topic even yesterday, and briefly we would want to touch upon the approach that we use to see this. So what is client-side collusion? Essentially, it's like two apps talking what they shouldn't be talking. So rephrasing it, we all know the concept of permission redelegation. So it's like, I have an app which takes my location permission. I have another app which doesn't take my location permission, but the other app has my location. Now, how does that happen? So we see this very commonly, that two apps can talk on Android using different things. Either, the side channels, as was talked about in the paper, 50 ways to leak the app by search. Or otherwise, we can have direct ways of communication, like you do content providers or you do broadcasts. So those are like valid ways which are allowed through Android, and two apps can use that to communicate and share the data which is allowed only by permission. So how apps interact with each other, that got us curious, and we wanted to find out different ways in which we can actually figure this thing out. So the challenges that come is that if you try to do static analysis of the code, the obfuscation sometimes is so heavy that it's really, we are unable to make sense of it, that, okay, these things is calling the content providers and sending it to the other app. So it gets tricky. How do we actually ensure it, that these two apps are talking? Other than, the different approaches of studying network traffic and then reverse engineering the apps, is there a different way in which we can find out two apps are talking? So the approaches that we took to study these kind of client-side collusion cases was first the sneak peek into the binder calls, and another one is the graphical way, which Dinesh will talk about. So let's talk about the binder calls. Now it's Android, right? Every inter-process communication goes through binder, which sits right in the kernel. So irrespective of code obfuscation, if any two apps are interacting, binder will always know. So whether it's through content provider or broadcast or anything else, the binder is the person who would know it, right? So now the question comes that, can we know what binder knows? So it turns out that yes, we can know it on a rooted system though. So either you need emulator or a rooted device. When you go to this particular path of sys/kernel debug binder proc, we see that there are a lot of log files which look like this, the text that appears on the screen. There's something called proc 770, which is kind of clear that 770 is a PID here. Then we have some rows with node, starting from node, and then we have other rows which are starting from reference. So it turns out that the node, the rows which start with node are the nodes being owned by this process, and the reference ones are the nodes which are owned by some other process and being referred by this particular process. So having this information, so we try to conduct an experiment on, can we find information out from these dumped logs? Now the problem here was like PIDs keep on changing, and they change. It's not that you kill the app and resume and the PID changes. PID just keeps on changing in between, like while the app is working as well, without any switch in the experience of the user. So if PID keeps on changing, our entire logic of finding out which app talks to whom will fail. So the approach that we took here was like keep polling the data. So we get all the proc files, and we get the output of the command PSA, which tells us which package has what PID at this particular point of time. And then we try to figure it out as to who's talking to whom. So here's a demo for that. So it's a basic bash script and a Python script. So we see that the interactions folder is empty. On the right side, we have this ADB shell. We have a device attached. The device is rooted. Now we do the ADB shell. Let's have a look at what is in the path we just talked about. So when we go to the path, we see a lot of log files. We picked up proc, but the other folders, which is the state stats, are equally interesting. In proc, we see all these things. These are basically files. The number is the process ID. And when we open this file, it looks like the one that we just talked about in the slide before. Similarly, when we do PSA, we get the PID and the name of the service or app or process which is executing, which is having that PID at that particular point of time. So we get output of this, this command, and we get all the proc files. And then we try to run the script. So once I run the script, we'll see that it'll fetch everything and try to make sense of it. So this is the output that we get. Every file is basically a process name. And then when we open it, we see what are the other services or processes that this particular app or service is talking to. So like for system server, it talks to most of the things. So you'll see a huge list here, and these are the things which it's talking to. So we found it a really interesting approach to study these kind of collisions. The final results of what we found, we'll be publishing it soon. The other way is the graphical way, which Dinesh will talk about.
Thanks, Aditi. Before we talk about the approach we have taken, I would like to talk a few minutes about the concept of knowledge graph. Next slide, please. Yeah, so knowledge graph, as most of us know, has been a very famous technique ever since 2014 when Google has popularized it as a concept. So it is basically an elegant way to consume graph-shaped data. When I say graph-shaped data, they are basically triples having two entities sharing a relationship between them. And the whole idea is to represent the entire knowledge about parsing an APK and documenting its behavior and its static relationships and properties in the form of nodes and edges. So that we create deeper connections among this structured data, and that really helps us from data to information to knowledge to wisdom path. For example, since as I've told in the introduction slide, this will be very useful in causal inference. Let's take a very simple example of difference between fact and truth. So often the intelligence system is able to derive intelligence, and how do we differentiate and provide reasoning? For example, this 3 + 2 that equals 5, it's a fact, whereas the reverse is not actually a fact, it is only a truth. 5 is equal to 3 + 2 can also be 5 is equal to 4 + 1 or 7 - 2 to infinite ways. So how do we differentiate these things? It is not only about similarity analysis, it is all about a combination of many things like similarity analysis, dissimilarity analysis, to track the evolution of how a PUA grows or evolves from one variant to another variant within the same family, how different variants behave and things like that. So the essential point here is with the proliferation of data in all the fields, the answers are everywhere. The answers are not a problem anymore. It is all about asking right questions, and knowledge graph is one such means to enable researchers to ask right questions or navigate the researchers to ask right questions. Next slide, please. So as you could see, we will also show you a live demo. The APK is parsed along with reinforced behavioral data as well with a node and the relationships. And you could clearly see in this case 2 samples, each having some specific attributes and some shared attributes. So the specific attributes are well just here because these are like adware. That means adlib embedded applications. So the specific attributes that you see is corresponding to the application code, whereas the shared genome that you see is the add SDK attributes. So between these 2 apps, the only similarity is the genes that share that comes from the advertisement SDKs. Let's quickly show you a demo like how this also can enable tracking intelligence and evolution of the samples and variants. So for this demo purpose, we are using a fantastic open source project called Kele. So generally, this knowledge graph is consumed better in an efficient manner through the client, through the command line version. I mean, Kele also has many Python bindings, JavaScript bindings, and things like that. But for better demonstration purpose, we are switching to the visualization mode. So as you could see in the screen here, currently we have plotted 2 samples in the graph format. And as I've emphasized, it is not only about what are the common things that gets shared between these 2 variants.
So I think we've lost your screen. Oh, there's back.
Oh, okay.
So Dinesh, you want to share the screen or we'll continue on this?
Yeah, thanks. Okay, I think I cannot start screen share while the other participant is sharing. Can you close the screen share?
Yeah, sure.
Okay.
Okay.
Yeah. Okay, so yeah, let me start the execution. So let's switch to the visualization mode, and we are plotting 2 samples in graph format. And as I emphasized, it is not only about the things, the attributes or the behavior that these 2 samples share in common. Some of the significant things can come from the difference as well. What is the dissimilarity index between these 2 samples? You could see this sample is almost similar with the other sample, with the only difference being voice recognition SDK. Now, for a researcher, this is an interesting piece of information. More than the similarity, it gives an indication that the sample has evolved to add voice recognition capability. So we may want to do a deeper analysis for this. So in a larger system, this becomes very useful, and we will show you a quick demo before we hand over to further sessions. So as you could see, the properties, how they are intertwined, and the similarity and dissimilarity index is calculated. So with that, I will again hand over to Aditi to talk about some of the privacy improving evolutions that has happened in Android over the past 10 years that has significantly improved the privacy landscape.
Sure. Thank you, Dinesh. I hope the slide is visible. Just navigating 1 second. So yeah, so we just saw what all kind of things we can get from knowledge graph, and that ends the client side collision techniques section. The things which can happen, the advantages that it gives us in the case are being discussed. So the first one is for sure the obfuscation kind of, you can not worry about that because you'll get to know if 2 apps are talking. But yeah, there are other problems that you would need to automate the operations on the app, and you would need rooted devices or emulators. So That was the conclusion. And now let's jump into the section evolution that improved privacy. So Google has been very active and has added a lot of amazing things in the Android ecosystem, which has helped prevent most of the things that we talked about in the previous slides, especially the case of like proc access denial. So previously, like any app can access the proc files, and you'll get to know about your network details, what all internet connections you made, because the TCP log was also there, and your ARP cache was there. So those files were like apps were able to access it, and with this setting, the denial has been made. And then there's a whole revamp dynamic permission model which has come into play, which will definitely change the scenario a lot, along with the deprecation of system windows and background app restrictions, changes to side loading policies, and changes to reflection access. So most of the things that we talked about, and the landscape is evolving, and a lot of things will be happening. So just excited to see how it goes, and at the same time, we'll keep on working on the things and share it with the community. So I think that marks the closure of the presentation. We would be very glad for any questions.
Great, thank you. So we're open for questions. So start thinking about questions you might have. We do have one question on Mattermost. It's from Renee. Renee, would you like to ask it, or would you like, or I can read it?
I can also ask myself if that'd
be great.
If you prefer that.
Yeah.
So thanks a lot for that talk, and particularly to Aditi for introducing or bringing up that topic of the potential of sharing data, not about just yourself, but about others that you may have data on explicitly or maybe even unintentionally, for example, in photos or wherever. Now, this transitive consent, as I tend to think about it, I have no idea how to deal with that. How did you analyze any particular ways of how you could raise awareness both for the users who actually do the sharing, that they might unintentionally share something about others, and maybe also raise awareness of those users whose data has been shared by others? Do you have any idea of what user interfaces could do to make this maybe more explicit, or to just point it out to users that, hey, this is something that you may need to consider when doing that? Or do you want to transitively ask the other people that you are sharing data about if they consent, if they're okay with that?
Yeah, so yeah, that is like an amazing question. Thank you for asking that. I don't have like concrete solutions, but I do have certain thoughts on that. We all know that awareness is for sure lacking, as in because it's like, when we deal in natural world, we know how to act when it comes to privacy. But when it comes to digital world, a lot of people see it as a device. They don't see it as a potentially privacy leaking gadget, right? So that understanding has to shift. I think it is happening, but more awareness is needed for sure. The way you present information to the user is one thing which tech industry is already working on, and I think it can be significantly improved. One basic thought was like, suppose when there's an accessibility service active on my device, right? I go to settings and I can see that these apps are watching, like these are enabled accessibility services. So if an app has accessibility service, it can see anything that happens on my screen, in fact, get all the text and do some actions as well, depending on what rights are there. So that information is available in the settings. When I installed the app, I had a look at it. And after that, I just use my mobile as is. So I'm talking about a normal user. And now when I'm going to suppose some browser and doing my searches, there's nothing on the screen that will make me aware that, okay, in the background, you know what, that app is also listening to what you're seeing, right? So that awareness is not there, and it's also not very visually present on the device itself. So that those kind of UX kind of changes I think we can do, so that we know that there's a conscious leaking of information. Again, other than that, I think it's more of a UX thing. I won't say we have technical solutions to it, because once data goes out, where it will go, what will that person who has the data do with that, we don't know. So we don't map how data flows across geos and across communities or orgs. So yeah, it's definitely challenging, but making the user understand through UX, a refined UX would be a good first step. So, rather than that terms and conditions like we see in web and we click, I agree, that instead of that, can you make it more visual? Or so why do we have to put it in text, right? If you make it more visual to make the person understand. So those kind of things, to me, it will lie more on the UX end as of now. But yeah, I'll refine my thoughts on that. Thank you for asking that.
Thank you.
So to augment Aditi's answer, apart from the server-side tracking that Aditi has shared her thoughts on, we are also looking at how some of the improvements can be done at the client side. For example, when the same crowdsourcing is being applied, we have common platforms, be it the system level intents that can get fired on the recipient of the person whose data, the third party's data, which is getting leaked between the user and the vendor. And we are conducting few researches in that area, and some of the experiments. Probably when we release the data, we will be able to release the efficacy of those models as well. So yeah.
Great. Do we have any other questions? We're about out of time, but I thought I'd kind of add something onto that. Are you guys familiar with the idea of contextual integrity? And thinking about, so if you're not familiar, this is something that Helen Nissenbaum at Cornell has been talking about for a number of years. And it's this notion that that users should allow the use of their data under certain contexts. Now, one of the things that computer scientists have a lot of trouble with, particularly security people, is saying, how do we allow functionality to happen without having strong controls over that? And so I would be curious what your thoughts on how those sorts of models might be incorporated into an ecosystem like this, and how that maybe relates to the topics we were just discussing.
If I interpret the query correctly, are we talking about how do we enable context-aware computing without having to give up a lot many data? Is that correct interpretation of your query?
No. So this notion of contextual integrity is if you're not familiar with it, it's not really defined context from the perspective that computer scientists often do, but it's more about the use of the data, right? Okay. So we allow software to use our data with certain assumptions, and when those applications violate those assumptions, then the contextual integrity is lost, right? And it's sort of about how do we inform the users how this information is going to be used, and then what ways might we be able to validate that? So thinking about some of the things you talked about at the end, right? You might be able to have other proofs of assurances that they're not going to sort of share this information with some other application.
Mm-hmm.
Yeah. So I think some of the areas can be covered using the server-side collusion analysis and client-side collusion analysis, like generative adversarial method. I think, Aditi, would you like to also pitch in with your opinion?
Yeah, so it's a very interesting thing. So data is actually, it is what it's worth for based on where it's used. So which context it's used for, as you just said. And I think one thing which definitely goes wrong is that user has no knowledge of, the algorithms running behind the scene, which will be using the data that the person has given and how it will affect it. So if anyone is asking a basic SMS permission, I give it, but then that app is reading my account transactions and deciding whether I'm eligible for loan or not. That thing I didn't know of, right? So that information needs to be, I think, communicated to the person who is sharing the data. I don't have a concrete answer on how we can do that. Again, it comes back to awareness, but or making it very clear in when the person installs the app. But I'm not sure how the developers would be doing that eventually. But yeah, that's a challenge. I think that is something that we have to address sooner or later.
Definitely a hard challenge. So I think we're about out of time for today. We can't hear everybody clapping, but if you can have some of a virtual clap Thank you, Aditya and Dinesh. That concludes our first talk. That's going to move us into the second talk of this session. We have Andrei Kovanov from Google, who's going to be diving down a bit further in the stack into the kernel itself. Andrei, if you'd like to share your screen.
Yeah, it's done. Can you see it?
No.
Give me a second. How about now?
Now we see it.
Okay,
Great.
perfect.
Take it away.
Okay, thank you. So thank you for allowing me to present on Android Security Symposium, and welcome to my talk about memory tagging for the Linux kernel. So my name is Andrei. I am employed by Google, and I mostly work on different bug finding tools for the Linux kernel. Since some time ago, actually also started doing work that is related to security exploit mitigations. And this is where memory tagging actually comes in. And so the plan for today is, first of all, I'm going to introduce my team. I'm going to tell you about different kinds of tools that we have for user space and for the kernel. The next part is going to be about memory tagging itself. I'm going to explain the concept. I'm going to I'm going to explain what is the current state of memory tagging in Linux and Android user space. And finally, the last part is going to be about the kernel. So my team actually consists of two parts. The first part works on user space, and there we have some bug finding tools like sanitizers. I think people who write C and C++ code have heard of them or have probably also used them. We have some tools that assist you with fuzzing, and one of the recent developments, we also have what's called GWIP ASAN, which is a sampling-based memory bug detector. And the idea is that you can actually use it in production to find memory bugs that happen in production code while it's running. The user space part of the team also works on mitigations like CFI, shadow call stack, and some of the others, and of course, memory tagging. Today, I'm going to be expanding more on Hwasan, which is hardware-assisted address sanitizer, and memory tagging itself, of course. So the second part of the team is where I work, and that part of the team actually works on kernel tools. For the kernel, we also have a set of sanitizers that allow you to find different kinds of bugs. I guess the oldest one is the address sanitizer that finds memory corruptions, and the newest one that was just merged into the mainline kernel a few months ago is KCSAN, which finds data races. We have Syscaller, which is our coverage guided fuzzer, and right now we're also working on KFans, which is something like GWIP ASAN, but for the kernel. So it's a sampling-based memory bug detector for production use. For mitigations in the kernel, first of all, we've been working on memory initialization, and with memory initialization, the idea is really simple. We want to initialize heap and stack memory to avoid leaking information from the kernel. And today I will mostly focus on a new Kasan mod, which is a software implementation of the memory tagging concept for the kernel, and it's called tag-based Kasan. So a typical point that's being made here is we do have a lot of software that's written in unsafe languages. And those unsafe languages allow you to do a lot of weird things. And as a result, you do get a lot of bugs and a lot of memory corruptions. As we know, some of the memory corruptions are exploitable. So instead of investing into fixing bugs, it makes sense to also invest into mitigation that will actually prevent those memory corruptions from being exploited. And one of the links that I have here is a link to our Sysbot dashboard. And Sysbot is an automation on top of Syscaller that essentially fuzzes the Linux kernel in the cloud. And currently we have almost 700 open bugs in the mainline Linux kernel. And the situation is not getting better in time. So memory tagging is one of the, it can be used as a security mitigation. And right now, let me explain you the concept. So the goal of memory tagging is to ensure that memory accesses are safe. The way this is done is by splitting the memory into memory granules, and each memory granule is associated with a tag, which is also sometimes called a color. Each pointer that points into memory also has an assigned tag. And the idea is to make sure that on every memory access, the tag on the pointer actually equals the tag on the memory. If they're not equal, then this raises an exception. And of course, depending on the implementation, you can have different sizes for memory granules. You can use different types of tags. Usually a tag is an integer, and the integer, you're using some bits to store it. The way this is typically implemented is the allocator does the following allocation. First of all, it has to align the allocation up to the granule size, because we cannot use, like, this is the smallest granularity that we have. Then the allocator chooses a random tag or uses some other rules to choose a tag. Tags the allocated memory, it tags the pointer, and returns the pointer. And of course, the pointer and the memory tagged with the same tag. On the allocation, we can retag the memory with a different tag. And then on memory access, what happens is we actually check that the pointer tag is the same as the memory tag. So here's a small example. Let's say we are allocating k bytes, and n is our granularity. And let's just say that k is actually more than n, which means that it's not enough to have one granule to hold k bytes, but it's enough to have two. So this is how the memory is going to look like. And here, each cell actually represents a memory granule, and our p pointer actually starts with address 0, our object of k bytes. So here we can see that the p pointer is tagged with the green tag or green color, and the two memory granules that hold the object of k bytes are also tagged with green, and this is what the allocator did. The other objects that are on this picture are tagged with different colors. So now let's say we're accessing byte number to n. Byte number to n actually lies in the next granule, and it has the color purple. But since we're using the pointer p, which is tagged with green, and the memory is tagged with purple, green does not equal purple, and here we have an out of bounds. Similarly, for a use after free, what happens is that after we free memory, we retag the granules that belong to the object, and here we use the red tag. And when the access to the object happens, we have the pointer that is tagged as green, we have the memory that is tagged as red, and since the tags are not the same, we do detect a memory access violation. So if you actually look at this picture and think about it, what's going to happen if our out-of-bound access actually still in the same granule as, still in the second granule, but is accessing past the k bytes. So in that sense, that access is not going to be detected, and our bug detection with memory tagging is actually probabilistic. So here's an example. Let's say that our memory granule size is 16, and let's say we use 4 bits to store a tag, which means we have 16 different tag values. And let's allocate 35 bytes. And when we're going to be accessing byte number 40, byte number 40 is going to be actually falling within the third granule. So to hold 35 bytes, we need 3 granules of size 16. And byte number 40 is within the third granule. So in this case, this access will not be detected. If you're going to be actually accessing the next granule, the fourth granule with offset 64, there is still a chance, if the tags are assigned randomly, that the tag on the next granule will actually match the tag on our object. And the chance of this is if we're assigning tags randomly is 1 out of 16. Here we can actually make sure, so it's up to the implementation, but the implementation can make sure that objects that are next to each other in memory actually get different tags. In this case, for linear buffer overflows, we can actually make sure that memory tagging always detects them. But if we're accessing a very, very far out of bounds, let's say we're accessing 100, 500, then there is no way for us to make sure that the tags are different, and there is still a chance that the tag is going to be the same. And the same happens with use of the free. So let's say we freed the pointer, but that's someone else allocated object on this place, and someone else retagged the memory with a random tag. So in this case, there is still 1 out of 16 chance that the tag on the memory will be the same as we had before. So now this was the description on concept, and a particular implementation of memory tagging has to address the following questions. First of all, we have to choose a particular granule size. We have to decide how many different tags we have and how many bits do we use to store a tag. We have to figure out how to assign and store pointer tags and how to assign and store memory tags. And finally, something has to perform the actual comparison of tags. So one of those questions I'm going to actually answer right now, how pointer tags are stored, because all of the implementations we'll be discussing today are going to be using the same approach. And this approach relies on ARM top byte ignore. ARM top byte ignore is an ARM feature that allows you, when enabled, to ignore. So the CPU actually ignores the top 8 bits of any address it dereferences. And you can enable it with setting the TBI bits in the TCR register, and there is a separate bit for the user space, there is a separate bit for the kernel. And since the top byte of any pointer is going to be ignored, we can store any value in the top byte, right? And this way we can actually store the tag that's assigned to the pointer in the top byte. Of course, the limit that we have here, since we can only use 1 byte, is that we have 8 bits per tag. So we can only use 256 different tag values. There are a few memory tagging implementations that are either exist or are in development right now. And the first one is the Spark ADI. And this one I'm not going to be discussing, but it actually exists in some Spark CPUs. It's implemented in hardware, and they use 4-bit tags and memory granules of 64 bytes. The one that I'm going to discuss on the next slide in details is ARM memory tagging extension, and it's being developed by ARM. And finally, right now, we actually have a partially software implementation of the memory tagging concept as a hardware-assisted address sanitizer. I say partially software because it still relies on the top byte ignore, but luckily top byte ignore is present in a lot of modern ARM CPUs. And I'm not going to discuss hardware-assisted address sanitizer right now, because in the third part of the talk, I'm going to be discussing its implementation for the kernel. And let's concentrate on memory tagging for now. So ARM memory tagging extension has been added in ARM v8.5 not very long ago. And right now, it only exists as a spec, so there is no actual hardware yet. And with ARM memory tagging, we have granule size of 16. And we have 4-bit tags for memory and for pointers. And the 4-bit tag is actually stored in the top byte, so ARM memory tagging also relies on the top byte ignore. With ARM memory tagging extension, the load and store instructions, they will actually compare tags in hardware and make sure that the tag on the pointer matches the tag on the memory. And of course, we have new instructions to manipulate the tags, like set tag values and stuff like that. If you think about it, we have 2 different applications for MTE. And the first one is we can make better and faster debugging and testing tools. For example, right now we have a software implementation, Hwasan, and we can actually change it to depend on MTE. It's still going to be a debugging tool, but instead of relying on software, it's going to be using the hardware, which is going to be faster. The same thing we can do for the kernel, and the same thing we can do for our sampling-based tools, for example. The second application is using MTE as a security mitigation, and it can be used in the kernel, it can be used in the user space. And I highly recommend looking at this paper by Microsoft, where they address, so they're trying to figure out what kind of exploitation techniques does memory tagging protect from. And there is also another interesting point, is that actually, when you have memory tagging, it turns out that you can, when you're setting the tag on the memory, you can initialize the memory at the same time without no extra cost. So you actually get memory tagging plus memory initialization for the same performance impact. And there is a link here you can follow and find out the details. So this is, let's say we're using memory tagging, or let's say we're using Hwasan in user space, and we have a problem. The problem is that when we use top byte ignore, the pointers, the user space pointers, will end up with top byte set. But the Linux kernel by default does not expect that. The Linux kernel only accepts user pointers that have 0 in the top byte. So to address this issue, a tagged address API was developed. It took a long time to figure out, but right now it's in the mainline kernel and has been backported to Android kernels 4.14, 4.19, and 5.4, of course. So this is required for Hwasan to work, and in the future will be required for MTE. And you can find out more details in the documentation link that I have here. But the general idea is that we just taught the kernel, we explained to the kernel that tagged user pointers are okay in certain cases. And here we come to the current state of MTE in user space. So first of all, for user space MTE, we do have the software implementation that works. And we do actually have an Android open source based image that includes user space apps built with Hwasan. And you can just download the image and you can flash it onto your Android device. And this, of course, requires what I mentioned on the last slide, the tagged address API, but this has been merged into Android common kernels. The second thing that we have that will be required for proper user space MTE is more kernel support. And more kernel support is in progress. There are patches on the mailing list and is being discussed for mainline inclusion. It's not in mainline yet, and it's not in Android yet, but hopefully will be at some point. And finally, ARM actually has an emulator that you can try to use, and it has MTE available. Okay, now we come to the third part of the talk, which is about software tag-based Hwasan. And initially, it was called kernel Hwasan, so we wanted to implement Hwasan for the kernel. But at some point, we decided to change the name to better integrate it with the current naming scheme that is used for Hwasan. And so for those who don't know, Hwasan is a memory bug detector for the Linux kernel. It can find out-of-bounds bugs on heap, stack, and globals, and it can find use after free bugs and some other types of issues, memory issues. It's really easy to use. The only thing that you need to do is to flip config Hwasan when you build the kernel, and that's it. Just build the kernel and run it. This tool is really useful in case you want to detect memory corruptions. So let's say you have some memory corruption and you're trying to track it down, but the problem quite often is that memory corruptions actually crash your kernel or your program at some random points because the memory is corrupted. And Hwasan tries to detect the corruption as early as possible, preferably at the point where the memory corruption occurred. So when it detects a memory corruption, it's going to print a report like this address was involved, this object was involved, here's the call trace, here was the object was allocated, here's when the object was freed in case it's a use after free, and all information like that. And it actually has a very moderate slowdown in memory overhead, so you can use it for testing, no problem. And with software tag-based Hwasan, we just added another mode to Hwasan that is based on hardware-assisted addressing. So the original mode that is now called generic is based on user space Hwasan, and the tag-based Hwasan is based on user space Hwasan. And the idea of the new name was, first of all, we rely on memory tagging, so that's why we called it tag-based. And the software part comes from the fact that this does not require any hardware implementation for memory tagging. It does it in software. In the future, we will hopefully have a hardware tag-based Hwasan, which will actually use hardware implementation in the form of MTE. And tag-based Hwasan can be enabled with config Hwasan SW tags, and it's been merged into mainline over a year ago, and it's been backported into Android 4.14, 4.19, and of course it's included in 5.4 since it's after it was merged into mainline. It currently only works with Clang, so it's not supported in GCC. And the original Hwasan mod that we had is now called generic, and the idea here is the original mode actually does not depend on any architecture, so it can be used for ARM, x86, it can be used for ARM, x86, and other architectures. There is quite a list right now, actually. Okay, so if you remember when we were discussing memory tagging, for a particular memory tagging implementation, we need to answer these questions. So I'm going to explain to you how Hwasan works and then present the answers to all of those questions. First of all, most of the sanitizers, I think even all of the sanitizers that we have, they actually consist of two parts. The first part is a compiler module that inserts instructions around each memory access, and those instructions actually, there are the function calls or actual instructions to make sure that the memory access is valid. And we have the runtime part that implements the hooks that are inserted by the compiler that has some annotations for the allocator. For example, in case of tag-based Kazan, we will need to mark the memory as tagged, right? And it puts all of the things together to actually detect bugs. So with tag-based Kazan, to store tags, we use shadow memory. And shadow memory is just a region of memory that is reserved specifically for Kazan. We use 1 byte tag for each 16 bytes of memory. Since the native kernel pointers actually have FF in their top byte, we initialize all shadow memory with FF. And when it comes to tag values, we actually do have two reserved tag values that are not being used when random tag are being generated. The first one is FF, because it's a native kernel pointer tag, like native kernel pointer top byte. And the second one is invalid, which is FE, and we use it for memory that is definitely inaccessible. For example, Kazan actually stores metadata per each allocated object, and this metadata stores handles to stack traces, allocation and deallocation stack traces, and we mark that metadata with FE. And we also mark freed object with the invalid tag. So this is how the shadow memory looks like. It's just basically part of address space, and the whole kernel address space linearly maps onto shadow memory. Since each 16 bytes of kernel memory have 1 byte of shadow, we just divide address by 16 or shift it by 4 and add the offset to calculate the address of the shadow memory byte based on the address of the kernel memory. This is the way allocator annotations look like. So let's say we have a kmalloc. Kmalloc is a kernel function that actually allocates memory, one of them at least. And by default, it just returns a pointer. With tag-based Kazan, we actually have a call around the return pointer, which is called here Kazan kmalloc. And that call is going to generate a random tag. It's going to tag the memory by setting the shadow memory. It's going to embed the generated tag into the top byte of the return pointer and return it. It also, of course, does other bookkeeping stuff like saving stack trace handles into the metadata and stuff like that. So since, and of course, also all of the objects are aligned to the granule size 16. And since all of the objects actually store metadata, we also have to increase the object size by the size of metadata. Kazan kfree, which is the annotation for the kfree function that frees memory, actually retags memory with the invalid tag. Here's a small example. In this case, I'm going to be using TBI to top byte ignore to show the tags. So let's say we're allocating 35 bytes with kmalloc, and let's say the random tag that kmalloc generated is 42. So the pointer has been tagged with 42 with green tag, and the top byte ignore says 42. And the object of size 35, when you allocate it in the kernel, it's going to use the kmalloc 64 cache. So 35 bytes actually requires 3 granules of size 16, and then there's going to be the 4th granule that is actually used to store Kazan metadata. And this is the way it's going to look in memory. And shadow memory will store the tag values for these memory granules. The 3 accessible memory granules are going to store the same value as the top byte of the pointer, which is 42. And the last granule is going to be marked with invalid as FE. And finally, when you free the memory is also retagged to invalid. And this is the way it looks in memory and in shadow memory. So let me answer the question that I've presented before. The granule size with tag-based Kazan is 16 bytes, like with MT. We have 256 different tags, but 2 of those are reserved. We have 8 bits to store a tag. And the tag, software tag-based Kazan uses TBI to embed tags into pointers top byte, and the tags are assigned an allocator and stored in shadow memory. And finally, the comparisons are performed by the compiler by the instruction that compiler inserts when compiling the kernel. Let's compare the overheads that we have for software tag-based Kazan and the old original generic mode of Kazan. The CPU overhead turned out to be almost the same, around 2x, but the memory overhead is completely different. First of all, when it comes to Kazan, memory overhead actually consists of a few parts, and the first part is actually slot memory usage overhead. And it comes from the fact that, first of all, we need to store metadata after the object, and then we have to also align the objects up to the granule size. And in case of generic Kazan, the overhead is actually 2x, but in case of tag-based Kazan, it's only 20%, which is extremely low. The second part that contributes to the memory overhead is the shadow memory. And with software tag-based Kazan, we have to use twice less shadow memory than with generic Kazan. And finally, tag-based Kazan does not require quarantine. Quarantine is a feature that generic Kazan uses to delay the reuse of memory and increase the chance of detecting use of the free. And software tag-based Kazan does not need it just by design. And putting all of this together, we come to the following conclusion that software tag-based Kazan is actually suitable for usage on actual testing devices. And we actually do that internally at Google. And yeah, something that I want to mention here is that if you get a device, we actually have an image, an Android image that has software tag-based Kazan for the kernel, and then Kvasan for the user space in the same image. And the device is usable. You can actually use it for day-to-day stuff, and it's perfect for testing. With the old generic Kazan, we actually had a problem since it required too much memory. Most of the time, it would make the device unusable. So currently what we have is the software implementation of memory tagging for the kernel in the form of software tag-based Kazan. Currently, it only covers the heap memory or the slab memory, how it's called in case of the kernel. And the first thing we would want to do is to add stack and global support for it as well, to be able to detect bugs in stack and globals. The stack is currently in progress, and globals will be addressed after that. The second part, after finishing this, would be to add a hardware mod for tag-based Kazan that is actually based on MTE, just to make it faster. And it's still going to be a debugging tool. And finally, the last step, which we will hopefully reach at some point, is to have the MTE implementation in the kernel and to have it usable as a production-grade mitigation technique. So this is the last part that is a call to action for people who actually write kernel code or for vendors who actually make Android devices. So first of all, please use Kazan for testing the kernel. And it's really easy to use, just flip the config and that's it. I realize that the testing story when it comes to the Linux kernel is complicated. So if you don't have any tests, any kernel tests, please make sure that device boots at least without any bug reports. The second 2 points are actually about using tag-based Kazan. And the 2 reasons that you want to do that, first of all, because tag-based Kazan is usable on testing devices. You can actually use it to find bugs that are not reproducible during testing, but are reproducible during the normal usage of a device. And we use it internally. And finally, a tag-based Kazan is a good way to prepare yourself for MTE because it's the software implementation of the same concept, right? So you can try it and try to find out whether your kernel code has any compatibilities with it, or whether your private drivers have some issues. And this will definitely simplify the future integration of in-kernel MTE. So this is the slides that I have. Thank you.
Wonderful, thank you. So we've got some time for questions. If we have anyone, I'm keeping an eye on both Mattermost and the Zoom chat, or if you want to raise your hand in Zoom. Renee, you're welcome to ask your question.
Thanks, Andre, for the excellent talk on introducing not only that specific KASM version, but the whole topic of memory tagging, which I think maybe may have been new to some developers, but is something that most of us will have to deal with in the near future. Now, what I was wondering is if Syscaller was now already able to find more kernel bugs by enabling KASAN in your kernel test cases, and if so, how does the Linux upstream kernel community react to another flurry of Syscaller bugs coming in?
Okay, I see. So Syscaller, actually, initially, we've developed the first version of Kasan, the generic Kasan, before we had Syscaller. So from the very first moment of using Syscaller, we actually had Kasan enabled on Syscaller. And with stack-based Kasan, we do not currently have an instance that is running on Sysbot in the cloud, because we do not have proper setup for fuzzing ARM kernels in the cloud yet. Actually, if you start using tag-based Kasan for fuzzing with Syscaller, I am not sure you're going to get many new bugs, because tag-based Kasan will not find like new types of issues in terms of memory safety. It might find new issues in terms of incompatibilities with using top byte ignore, for example. But the bugs, the memory safety issues for generic Kasan and tag-based Kasan are the same classes of issues. And since tag-based Kasan is actually a little bit weaker than generic Kasan, because the generic Kasan has more capability of detecting really small out-of-bounds accesses. So the main use case for tag-based Kasan is not actually fuzzing. I mean, it can actually be really useful for fuzzing on actual Android devices if you ever do that, because generic Kasan can make the device really slow and unusable, and tag-based Kasan should allow the device to keep up. So you can use it for fuzzing on devices. But for fuzzing in the cloud, I don't think it's going to be very useful.
Thanks for clarifying.
So as other folks are thinking of potential questions, so again, thank you for the great overview of the topic. It's an area that I'm not particularly familiar with, and I learned a lot throughout the talk. You know, one of the things that you mentioned was there's slowly becoming more and more hardware support for doing these tests. As this hardware support becomes more widely available, do you see potential for these techniques to possibly be used more generally as a runtime defense, or is this always going to be a testing sort of capability?
Yeah, so my hope is that eventually we'll have, in particular, memory tagging be used as a mitigation and not only for testing. It's like the ultimate goal is to actually have it to be used as a mitigation.
So in that context then, and one of the early slides you had talking about how the tagging works and the limitations of what you can actually put in the tag size, it became somewhat probabilistic. Am I right?
Correct.
So if you think about, you know, probabilistic defenses, of course, are useful, right? ASLR is tremendously useful, but there are ways of getting around ASLR by just trying lots and lots of times. Do you see similar sorts of issues here, or is it the fact that this would be in the kernel make it less so because it's not scalable to try as many times as you would need?
Yes, so there are, of course, the probabilistic nature of MT makes it possible to bypass in certain cases. And the initial version that we will have will probably, be vulnerable to those. And okay, I'm going to split it into parts. First of all, about the probabilistic nature. So there are some modifications that you can do to memory tagging to make sure that certain bug classes are detected with 100% probability. For example, what I've mentioned with assigning different tags to memory objects that are next to each other in memory. And you can just make sure that the tags are different. For example, you can keep generating a new random tag until you get a tag that is different from the ones that are around those, right? For use after freeze, there is actually a discussion right now. It's mostly being discussed for user space MTE. I'm not sure if this will be applicable to the kernel. It's about, so those who are interested, you can search for a Mark Us paper. It's called like Mark Us. And so I'm not going to go into details, but the idea is that there is an approach that will actually allow you to detect use of the freeze with something very, very close to 100% probability, maybe even 100%, and without any additional impact. And when it comes to the kernel, actually bypassing MTE when exploiting a bug will be, when we have MTE, will be a very interesting topic for research. And in kernel work, of course, have less flexibility in terms of that we cannot retry to exploit a particular box 100 times, because the first time kernel crashes, it's just going to crash. It's not a user space process, a user space daemon that will just be restarted, right? So in this case, attacking the kernel is harder. And what I remember is that one of the talks of Jan Horn, who is a Project Zero security researcher that works on Linux kernel, he actually mentioned that a particular way that a user might be able to extract tags from the kernel, and by using a particular syscall that allows you to predict whether two regions of memory actually have the same tag. So there are going to be attacks like that for sure. And the probabilistic nature of MT, of course, makes it not 100%, not 100% protection from everything. But my understanding, based on my experiences writing kernel exploits, is that this is going to make writing kernel exploits an order of magnitude harder, or maybe even more.
That's awesome. So we've got a question on Mattermost, kind of two-part question. The first part might be the conference organizers, but whether or not the slides will be available.
Yes, I will publish them on Twitter in like 10 minutes after the end.
Great. And then the second question, which you touched on a little bit kind of informally, but I think the question is a bit more specific. Martin's asking what the expected overhead for hardware implementation is on a mobile device.
Yeah, it's a good question. Before we have the actual hardware implementation, no one knows yet, but the expectation is to have it in, like, it's usually been expressed as a single-digit % impact, something like this. So it's less than 10%.
Okay. All right, well, excellent talk, and thank you for all of the answers to the questions. I think that concludes, well, first, virtual round of applause for Andre, wonderful talk. That concludes the first session of today. We now have a break for the next 50 minutes, I believe, going until 16:30 CEST, at which point we'll pick back up with an excellent keynote from Alex Gutman from Qualcomm. Thank you, everyone, and see you soon.
Welcome everybody again for our session, for our second session today. The first keynote, which will be given by Alex Gantman, who is the Vice President of Engineering at Qualcomm Technologies and has been responsible for the security of Qualcomm products for quite some time. Alex is also one of the main hosts of the Qualcomm Mobile Security Summit, which has, as many of you will probably know, always addressed a very similar community to the Android Security Symposium. And if I'm informed correctly, the next edition of this Qualcomm Security Summit will be held in 2021. And we'll, of course, as organizers, will do our best not to have it collide as it so nearly did sometime in the past. With that, we're very much looking forward to your talk. Alex, over to you and to San Diego.
All right, thank you. Let me make sure I'm sharing my presentation. Can you see my slides? Oh, not yet, hold on. There we go.
Can see it now, thank you.
Okay, you can see it, you can hear me. All right, so thank you, Renee, for the introduction. Thanks for hosting me. When Renee invited me to speak, I asked him, okay, so what do you want me to talk about? He told me like anything you want to. So you kind of have to be careful what you wish for. So I reflected on, what can I talk about? And I wanted to talk about how I've seen kind of how my thinking about the evolution of security in the products that we make has evolved or has progressed. How I see that security evolving, and kind of what I see we can do to improve and accelerate that process. Let me see. Okay, quick intro, on top of what Renee already said. Like Renee said, my name is Alex. I work at Qualcomm. I've been at Qualcomm essentially, forever, since the end of last century. I joined as an intern. Here's before and after. I think Qualcomm has been pretty good to me. I think I've been, some use to Qualcomm as well. I've been working on security there basically since 2000. So I spent the last 20 years working on improving the security of mobile products. Used to be a real security engineer. These days, I mostly make slides badly. Few disclosures. It's still early here, so technically I haven't clocked in yet. So I'm here in my personal capacity, right? I'm going to be sharing some personal opinions. Please don't attribute them to Qualcomm. Please don't get me in trouble with my management. So I wanted to do something different today. I wanted to give an optimistic security talk because I'm that rarest of unicorns, an optimistic security engineer. This may come as somewhat of a surprise to those of you that know me, because I do try to maintain a fairly kind of solid facade of skepticism and devil's advocacy. But that's mostly just so that I can pass myself off as a real security engineer and fit in with my peers. In fact, I have the distinct honor of having been called the most depressing person he has ever met by Chris Evans. This was back when Chris led Google's Project Zero. And I think at some conference over drinks, I tried to explain how patching works in the mobile ecosystem to him. But nonetheless, I assure you, kind of deep at heart, I'm an optimist. And that optimism is not born of any sense of naivete, right? I've spent enough years in this industry to feel like I've really been, I've seen inside the total perspective vortex. I've seen the kind of the unimaginable infinite complexity of the mobile ecosystem and my own insignificance within it. A tiny marker, a microscopic dot on a microscopic dot that says you are here. But in spite of that, or as I'll talk more perhaps because of that, I have developed a rather kind of optimistic outlook. So I understand that kind of a cheery security engineer is a bit of an oxymoron and does not naturally engender trust and confidence. So I must first build up some credibility with this audience by basically, scaring you and telling you how everything is broken. So here we go. Okay, we're all doomed. Hold on, let me make this better. Okay, okay, there we go. Okay, so we're all doomed, and I have to admit, kind of, I was putting the slides together. This is not as shocking these days as it used to be, because now you open the news and you have this like infinite array of choices to be doomed by. But that aside, I'm talking about a very specific thing, particularly that we're doomed to never fully understand our own creations. And it's kind of, for engineers, it's hard to accept, right? Because as engineers, we have this God complex, right? Like, we're the creators. Like, I created this thing, and as the creator of this thing, I should be able to create it just to do exactly what I want and just what I want. Moreover, like, there's almost like a sense of entitlement that just because you create it, you have to really understand how it works. And it's not really kind of this sense of entitlement is not really supported by available evidence, right? This is kind of one cute counterexample. Like, any idiot can make one. Like, we made two, still have no idea how they work, right? Although, granted, this is a little bit out of realm of engineering. But the reason we will never fully understand our own creations is complexity, right? This is a somewhat random picture I got when I Googled for software complexity. This is a chart of relationships between classes in the Hibernate Java library, right? And you have to keep in mind that this in itself is, again, just a microscopic dot on a microscopic dot within some larger system, right? And kind of the details don't matter, right? I just wanted to illustrate, something that shows complexity. Perhaps a better choice would have been kind of like a modern system on a, the diagram of a modern system on a chip, but that would require me to talk to way too many lawyers. So I just Googled for something instead. So basically, and the complexity of the things that we're creating, the complexity of technological creations, is kind of rapidly approaching the complexity of living organisms. If you look at the kind of the number of transistors in modern systems, the number of bits of state in software, it is immense. And ironically, the very mechanism we use to cope with this complexity and to build even more complexity is the very thing that limits our understanding of what it is that we've built. And I'm talking about abstractions, right? Because abstractions provide a simplified model of the system, right? They provide a simplified model of the layer below to enable the builder, the designer, the engineer, kind of to free up their cognitive capacity to deal with more complexity at the layer above. And the keyword here is simplified, right? The kind of the paradox of the abstraction is that it can only be useful if it is wrong. Because if it doesn't simplify, if it doesn't hide some information, it doesn't provide its kind of core value. So I like to use this diagram to illustrate the point, right? We have a nice kind of simplified abstraction, straight lines, right angles on the left. We have reality, which is still a very simplified view, but bear with me, right? It's a bit more complex, right? You have the curved corners that are harder to model. And obviously, if you overlay the two, there's going to be some delta. And in our field, there's a very specific technical term for that difference between abstraction and reality, right? Like, we call it a vulnerability. And if you think about it, really, most, if not all, types of vulnerabilities fit this metaphor pretty well, right? So, like, we miss buffer overflow vulnerabilities because the abstraction of a function call hides the kind of the detail of passing the return address through the stack. And we miss integer overflow vulnerabilities because the abstraction of arithmetic in C and its derivatives looks so much like the arithmetic we learned in primary school and hides the truncation and wraparound of the modular arithmetic underneath. And then we miss things like rowhammer because the abstraction of linear random access memory hides all the details of the physics of DRAM and how that works. In fact, this is also the reason why, in my view, so much of the security education is really about unlearning the lies taught in the core computer science curriculum. Okay. So an abstraction, I should say, by the way, right, and if you zoom in, kind of this problem is fractal, right? Because again, the difference between abstraction and reality, reality is very messy, right? Like it doesn't have nice kind of straight lines. And again, the more you zoom in, the more kind of delta you see. So what happens is, right, like as a builder of a system, right, the designer thinks that they're working on kind of these solid layers, solid bricks with kind of no gaps between them that all fit in. And in reality, all of these vulnerabilities. And Sergey Brodus has this very eloquent saying: layers of abstraction become boundaries of competence. And that is, of course, what they're meant to be, right? Again, the abstraction is meant to hide the complexity of the layer beneath. But that means that kind of a person working at the top of this pyramid, right? Like, so a developer working on a cat filter for your, for some camera app, will never understand the full complexity, the full details of the entire system below, right? The language runtime garbage collection and the operating system permission model, and the CPU cache hierarchy, and the physics of DRAM and the chemistry of silicon dopants in the in the chip, right? It's not going to happen. Like, they will never understand the full thing. Like, and none of us will really fully understand how our computers work. But that's how modern technology kind of advances, right? Like, we keep adding layer upon layer onto this kind of tower, and really it's all kind of tightly packed layers. It's not just layers of abstraction, it's tightly packed layers of vulnerabilities. Okay. So hopefully that was sufficiently kind of demoralizing to convince you that I am indeed like a real security professional. And normally this is where a security talk would end, right? We're doomed. Thank you. Please don't forget to follow me on Twitter. Okay, I believe we have some time for Q&A. And that used to be me, right? Like, early on in my career, I actually got the nickname Dr. Evil. This was the early 2000s. Austin Powers movies were still popular. And I picked up a reputation for coming up with essentially these like movie plot business models, for $1 billion that attackers could build by exploiting different vulnerabilities. And keep in mind, this was before we could just say, hey, it's a bug, fix it, right? When we had to go through the whole dance of, well, but why would anybody ever do that? Luckily, we've sort of moved on from that largely. So anyway, like I said, so I got this nickname for all my dire predictions of how things will go wrong, and things were getting fixed, right? Like we had some success, but things are never fixed as quickly as you would hope. So I was perpetually worried about all of my dire predictions coming true. But years went by, and people went online and they banked and they shopped, and there was some crime, but there's always crime, and the overall crime rate went down. And like, cities did not burn down, or cities didn't burn, financial system did not collapse. Well, okay, like all of those things happened, but none of it happened because of a buffer overflow in the phone or anything like that, or in software at all. So after a while, I had to reconcile with the fact that the world kept on spinning. And that's what led me to kind of my current sunny outlook. That, a realization that despite all of this complexity, like even if we can't understand it, right? But despite all of that complexity, the products that we make, evolve a kind of resilience to the threats that they face in the world around them, almost like living organisms. So hopefully, some of you recognized the title of my talk, The Evolution of Secure Things, as a reference to Henry Petroski's book, The Evolution of Useful Things. And in this book, Petroski lays out the history of how kind of common household objects like the paperclip and the fork came, to look the way they look. How did they get their current shapes? And essentially, his central thesis is that form does not follow function, but form follows failure. And what he means by that is you don't get the shape of a paperclip, for example, by getting some smart person to sit down and think really hard about kind of, okay, what's the ideal kind of minimalist tool or mechanism that can hold a few loose leaves of paper together. Right. The way you get a paperclip is through, or anything else is through many generations of kind of iterative trial and error, right? Somebody comes up with something and it works kind of okay, but then people observe the ways in which it is lacking and they try to improve on it. Like more precisely, kind of not every alteration is an improvement, right? Some alterations lead you kind of to an evolutionary dead end, but this, the process of, trying and seeing what sticks and what makes things better is what eventually leads you to some ideal shape. Now, notably, he points out that this evolutionary process doesn't necessarily converge on one ideal form factor, right? On one ideal shape. The kind of most obvious example are eating utensils, right? This is, the problem of conveying food from, plate to mouth is all this time. This is something humans have been doing forever, and yet we see different cultures come up with vastly different tools for the problem, right? Again, most notably the fork and chopsticks. Right? So it's not like there's one ideal solution. You can have multiple solutions, and which one you end up with kind of depends on the evolutionary path you take. And when I read this book, I was struck by how much about Petrovsky's description about the evolution of everyday things resonated with me and kind of reminded me of how I view the evolution of security of things, right? Again, the similar thing is, how we keep trying things and we keep improving on the failures of the shortcomings of the past generation. And, I think some people view it as a failure of our profession that we don't get things right on the first try. But I'm not sure anything other than this kind of evolutionary approach is really reasonable to expect. And moreover, with most evolutionary processes, the outcomes are far better than they have any right to be. Right? And I think over time, commodity computers have become very resilient to the common threats around them. And look, they'll never be perfect, right? And there are always gaps, but they continue to evolve. I think understanding the evolutionary forces in play can help us speed up the process. And one of the most, I think, critical forces in play is consumer demand. So I believe that in consumer markets, in particular, security can be a differentiator. Security does become a differentiator, but it is the last differentiator, meaning that it really begins to impact purchasing decisions only after the rate of introduction of new features slows down. So, when the product becomes commoditized, right? Like when all products more or less look the same, then people want reliability, security, and the broader reliability and safety. And we can look at a few historical examples, right? I think if you remember what it was like to buy a PC in the 90s, right? By the time you brought it home and finished setting it up, it was essentially an outdated pile of junk, right? Like you could go back to the store a few weeks later, buy something that was twice as fast for half the price. It's, every you would longingly look at every ad that came in about, what new computers are available and, keep dreaming about when you can upgrade. So in that climate, every time something went wrong, every time you had a crash, every time you had a virus infection, it was annoying, it was frustrating, and it was one more excuse to do what you really wanted, which is to get rid of this one and go buy a new one. Okay. Then at around 2000, the hardware is fast enough we get out of order execution CPUs, we get hyper-threading, great things, never look back, right? The operating system is stable enough. Productivity software is great. Office has all the features you would ever want, plus the paperclip thingy that pops up. And all of a sudden, you don't want a new one. You want this one to keep working, right? Like, yeah, you could go buy a new one, and the plastic is a bit nicer, and the screen is a little bit crisper. But suddenly upgrading is a chore. You have to move all of your files and reinstall all your apps and reconfigure all the settings. It's like, I just want this one to work, right? And so I think it's not a coincidence that Microsoft's big, trustworthy computing push, they're rolling out of their secure development lifecycle, came around that time, right? Bill Gates' trustworthy computing memo came out in early 2002. I think a similar thing can be observed in the automotive industry. And I know car comparisons are dicey, but kind of bear with me. And I apologize, a lot of my examples are going to be US centric, but I think they, hopefully they kind of carry over to other places as well. But at least in the US, right, kind of looking at the data, widespread availability of convenience features like FM radio and air conditioning and automatic transmission predate availability of safety features like seat belts and airbags and anti-lock brakes. And again, as I said, like even the basics like seat belts. And it's only kind of after cars become commoditized, right? So, what I remember about, for example, car commercials in the 90s and the early 2000s, they weren't advertising different features. They were all advertising crash safety ratings and warranty, periods, how long the warranty is, right? So by that time, all the focus has shifted to safety and reliability. That's at least until the more recent automotive renaissance based on computation and connectivity. And I think it wasn't all, Bucktrack and Ralph Nader either, right? Without dismissing or diminishing the role of activism, I think it's important for us to recognize the other forces in play and to understand why advocacy efforts succeeded at the point that they did. Right? Because it wasn't like Windows security was great throughout the 90s and nobody said anything, right? It wasn't like there wasn't, pressure on Microsoft to do something about it. And prior to Nader's book coming out, it wasn't like people weren't dying by tens of thousands every year in the US alone for decades leading up to that period. But something else happened in the market at that time to allow that transition. And I think we're seeing a similar thing with smartphones now, right? As we've made the transition from, so I would argue that today the smartphone is the most secure device, digital device that most people own, right? And it wasn't the case, 25, 20, 15, even 10 years ago, right? Probably, maybe even 5, I'm not sure about that. But, once the rate of introduction, introduction of new features has flattened out, we saw this rather sharp transition of key market players to focus on security. And it's easy to forget how sudden that change was and that it wasn't always like that. And it kind of makes sense when you think about it, both from the vendor and from the consumer point of view, right? So from the vendor point of view, security is not free, right? Security does cost money, and it costs time to market. So when you're in the mode where the rate of innovation is high and people want new features, and there's people are lining up around the block on product release day. Right? A vendor that delays the release of their product to add more security in without kind of increasing the feature set, and that's almost a suicidal move. Right? And at the same time, right, like looking at it from the customer perspective, we can see it as potentially a rational choice as well, though not necessarily kind of conscious and explicitly thought out. Because if you look at security as the ratio of benefit to risk, then during periods of rapid innovation, your best way to optimize that ratio may be to capitalize on the skyrocketing benefit, right? And it's only once that flattens out that your only way to improve that ratio begins to now kind of decrease the denominator and to draw down the risk. And look, this forum, I think, provides us with a perfect example, right? We're doing this on Zoom, right? Zoom is not exactly known for their security first posture. And yet the organizers, despite their considerable security expertise, decided that the features offered by the platform outweigh whatever security risks it brings. So clearly, from a business perspective, Zoom made the right call. Now having captured significant market share, they can afford to invest in security and make the program better, make the tool better. And of course, in essence, as consumers, we have endorsed that choice because that's the tool we chose to use. We didn't choose something that focused on security instead. And I think so cases like Zoom, right, bring up the question, okay, well, why can't vendors focus on security earlier on? Like, why don't we see more companies kind of, why do they leave it until the last minute? I think pictures like this help us to understand why, right? So this is, most of you are probably familiar with this picture. This is kind of the canonical illustration of survivorship bias. So during the Second World War, US military wanted to know where they should reinforce their planes, their bombers. And so they surveyed planes coming back from missions, and they mapped out all the areas that got hit by enemy gunfire, and they created this sort of heat map. And the initial proposal was, okay, well, clearly we have to reinforce the areas that are getting hit more. Until a statistician looked at it and pointed out that they're only looking at planes that survived the damage and returned to base, right? The areas that are blank on this chart, it's not like enemy fire is miraculously missing those parts of the plane. The more likely explanation is that when that part of the plane gets hit, it is fatal, right? And planes that get hit in those places do not return to base. So rather than dealing with damage that's not fatal, that can be dealt with after the plane returns, they have to armor the places that are left blank here. So how does it relate to the topic that we were discussing? So I think similarly, I think there are lots of companies that focus on security early on. Unfortunately, the choices that we make as consumers, unfortunately, or maybe I shouldn't assign a value judgment to, but the choices we make as consumers, these companies don't often survive long enough for us to know their names, right? Early on, focus tends to be on usability and features and things that consumers want and the benefit that they can get out of it. And only after that, companies begin to focus on security. Now, there's another reason why I think security takes this, go through this evolutionary process. And that's because the product itself evolves. You can't secure it until you know what it is. So like this is one of the early Qualcomm phones. I love this phone, by the way, probably still one of kind of my favorite phones of all time. But properly, kind of quote unquote, properly securing this phone in 1995 would have precluded pretty much every feature of a modern smartphone, right? Like, I mean, I can imagine a conversation. Right? Let me get this straight. You want to connect this thing to the internet, and you want to allow people to run third-party code on it. And I remember those concerns, right? I remember as phones began to add more and more features, camera and apps and so on. There were many kind of, especially within the security community, there was angst and concern that kind of this is greatly expanding the attack surface, which was correct. right? And people were saying, look, I just want a single purpose device. I want the phone to be a phone and nothing else. And while, again, as a security engineer, like those concerns were valid. Yes, the attack surface of a modern device is much greater than if a phone 20, 25 years ago. And yet, miraculously, I claim it is much harder to get remote code execution on a modern device than it is on the phone from 1995. So somehow this system of evolution works remarkably well. And I claim that actually the security of consumer devices has been a huge success. In fact, I'll go a giant leap further. I will claim that the software in consumer devices today is more resilient than anything the consumer market has ever seen. So think about some of the things you have in your house, right? Like an armchair, coffee maker, this is a bag, but say imagine glasses. I'm assuming everybody in this audience has glasses, eyeglasses. And these are all things designed for household use. They look nice, they provide excellent functionality, they're priced right for their target market, and so on. But they also all require careful handling, right? Like they're not designed to be abused in any way. I like to say there's nothing in my house that can survive a 3-year-old with scissors. Nothing. In fact, like the entire phrase, this is why we can't have nice things, is based on the premise that nice things require careful handling, and and if we don't handle them really carefully, then they break. Now, there's another class of products that is meant to go into public spaces, like a park bench, train station vending machine, a shopping cart, right? These things are bulkier, they don't look as nice, they're not, the functionality they provide is very, very limited. They're a lot more expensive, but they can take some beating, right? They can take a scratch, maybe a baseball bat here or there. So the interesting thing is things like phones, like smartphones, are in both places at once, right? On the one hand, this is a consumer device. It has to feel nice and look nice and provide great functionality and be reasonably priced. On the other hand, the software it runs is connected to the internet, so it's essentially in the public space all of the time. And we now have this expectation that the software should be able to withstand not just kind of casual abuse from hyperactive kids and bored teenagers, but even targeted attacks from trained professionals. Now, pause for a minute to think about the significance of this change. This is a fundamentally different expectation than consumer goods, than we've ever had for consumer goods before. And really, I didn't think this was possible, right? Like, in fact, I looked at my notes. I have notes back from 2011 where I postulate that, consumer goods, including software, cannot be made vandal-proof because I just couldn't find a suitable preference. But, here we are. I mean, look at this chart from Zero View. And I know it's a marketing slide and we have to take it with a grain of salt, but what else in your house costs upwards of $2 million to break? Okay, and maybe remote attacks are not a fair comparison. Like, look even at basics like pin bypass and local privilege escalation. Like, who has a lock that costs $100,000 to pick? Who has a door that costs $200,000 to break down? Like, it doesn't happen. Right? So I think this is incredible, and I still find it hard to come to terms with this. Right? So I think whatever process is in play here is clearly producing very good results. And like, I'm not trying to say that, look, we just should sit back and enjoy the ride. I think we should look at what can we do to accelerate this process. And evolution works by iteratively trying new mutations and seeing what works and adopting that, right? So for it, you need two things, right? You need a useful utility function, some sort of a feedback metric. So whether it's survival in in biology or path coverage and fuzzing or whatever it is, right? But something to tell us that we're moving in the right direction. And and we want fast iteration. Now, I think in the context that we're describing, the speed of iteration is not an issue. I think we're iterating fast enough. I don't think we have a problem with how often, how fast products come out, how fast we try new things. But I do think we have a problem with the utility function. I think the feedback mechanism that the market provides kind of works, but it's really slow and imprecise. Right? We never really know why a product fails. Whether it's because of a lack of security or because of something else. So what we really want is some sort of rapid, accurate feedback to see if the change that we've introduced has made a thing more secure. And remarkably, kind of mind-bogglingly, we have no real way of assessing the security of the thing. And it's just mind-boggling that we've gotten this far in this field without being able to answer such a basic question. And in fact, so I'm going to do something now. I'm actually going to contradict something I said earlier, but it's a keynote, and I believe I'm allowed to do that. So I'm going to claim that we actually have no idea if computers are more secure today than they were 20 years ago. So kind of follow me in this brief diversion. So let me ask this question about cars, and car analogy again. Sorry. A car is safer to drive today than they were 40 years ago. How would we answer this question? Right? Well, we can look at safety features, but safety features only tell us that somebody's trying. We don't necessarily know if they have an impact. We can look at safety tests. Again, safety tests, somewhat predictive. Like we think this helps, but we don't really know if that, if a car that does well in a safety test actually results in kind of a safer experience on the road. So ideally, what we have is actual data, like actual measurement of harm, right? So in the US, we have this data from the National Highway Traffic Safety Administration, NHTSA, right? And we can look at fatalities per year. And we can see that, yes, from the 1970s to today, the number of fatalities per year has decreased significantly. Now, there's a complication, of course, because the usage during that time has changed a lot as well, right? The number of people, the number of cars, the amount that people drive has increased drastically as well. So ideally, we normalize this kind of units of harm by units of benefit. So let's say we divide it by vehicle miles traveled, right? And when we look at those stats, we see that the change is even more drastic, right? There's almost a threefold decrease in the number of fatalities per mile traveled from the 1970s to today. So, so we can look at this data and say, okay, great, there's been progress. Now, we don't necessarily know specifically what led to that improvement, whether that was, speed limits or strong enforcement of traffic laws or seat belts or, global warming, whatever it was, right? But we can clearly see that there was improvement. So now we ask the same question about computers. Are computers more secure today than they were, let's say 25 years ago? So how would we answer that question? Like, what is the data that we would support our response? Like, what is our measure of harm? Like, we can't even agree on what units to use, right? Is it like ideally somewhere, right? Like we should be able to say, look, this hopefully 0 lives lost, but some measure of physical harm, some measure of financial harm, and then we want to again normalize it by measure of benefit. And I have no idea how we, like what units we would use for benefit, right? Is it per number of transistors in the world, per number of bytes received or transmitted, whatever it is, right? And not having this, not being able to answer this question is really quite bad. In fact, like I think this is the biggest thing holding back our field. Now, personally, I try to ask myself questions like, okay, so if my budget was doubled tomorrow, like how would the users notice? Like what can the user points to say that, okay, their phone really got more secure? And I like to think that I'm in the business of harm reduction, right, or crime prevention. But I can't tell, to what extent I'm succeeding without data like this, right? And so, the automotive industry has NHTSA data on car fatalities that they can use to assess progress on car safety. And, the healthcare industry has CDC data on infections that they can assess improvements in disease prevention. And in the security industry, we have thought leaders, right? And for what we lack in evidence of what works, we more than make up for with like really strongly held fanatical beliefs about what should work. So I can try, we have a lot of, we have maturity models and best practices and guidelines, and I can measure adherence to those. But if I do that, my job is not about harm reduction. My job is about compliance. I don't want to be in compliance, right? We can look at kind of decreasing negative press coverage based on CVEs or conference talks, but then my job is PR, and I don't want my job to be PR, right? Look, I know great people that work in PR. Some of my friends work in PR. That's just not my career choice. I want to be in the business of harm reduction, and for that, I need to be able to measure the actual outcome of my work. I know now that there are things like the cyber ITL, right, that look at, analyze the binary or analyze the product and look at which countermeasures are enabled, which unsafe functions are still in use and so on. But again, those things are like looking at safety features, right? It measures effort. How hard is a vendor trying to make their product secure? It doesn't necessarily tell you what the end outcome is. So in some sense, kind of going back to Zerodium's marketing slide, in some sense, this is the best feedback mechanism we have. And it's not a bad one, but it's not ideal, right? Like, and it's hard to tell how accurate it is. So kind of, I'm coming to the end here. I know we don't have a lot of time. So wrapping up, overall, kind of, when I look back at this slide, right, this is a very kind of happy, optimistic slide. Like, those are great numbers on the left-hand side to be looking at, right? And I hope, so looking at this, like, I hope that I've managed to deliver a somewhat optimistic talk, at least kind of by the security talk standards, and convince you that it's not all doom and gloom, and that consumer products are continuously evolving and becoming more secure, and that your smartphone is arguably the most secure device that you have. We can see the effect of this evolution, like even our threat models are evolving, right? To the point that, like, today, nation state attackers are explicitly part of the threat model. It wasn't like this. It wasn't always like this. It wasn't like this even 15, maybe even 10 years ago, right? Like, I remember starting out in this industry, and it was like an explicit position when you're performing a security analysis, when you're doing threat model. Government attackers are out of scope because there's not much you can do, and we've moved on since then. Now, I'm not saying we're successfully stopping every government attacker, but it's a realistic goal. It's a bar that we're actively trying to reach for, and that is a huge change for the better. So when I look at new kind of new fields like IoT, for example, I get a sense of deja vu, right? Because I see many of the same concerns coming up as what I was seeing during the early days of mobile. Many of the same concerns that I was raising during the early days of mobile. So, and knowing how that turned out gives me hope, right? So even as I share a lot of the concerns about the state of IoT security, I remain very optimistic about the fate, right? But that product category needs some time to mature and stabilize, to evolve, and then security of it will evolve too. Now, the reason I think you should kind of believe and embrace my optimistic outlook is my track record of being wrong. Okay, that sounded a bit better in my head the first time around. What I mean is, it's not just sort of some random thought I had, it is a conclusion based on a falsified hypothesis. In fact, a many years worth of falsified hypothesis. Because I used to believe something different, and those different beliefs did not pan out, right? So I reconsidered them, and this is my new outlook. So really, it's science, really. Okay, and I think that's actually it. So, those were the thoughts I wanted to share with you today. And I think we have some time for Q&A.
Thanks a lot, Alex. I was right in telling you that you could talk about anything you wanted. This was a great keynote. Thanks for being one of the remaining optimistic security experts here in the round, because we do need that at conferences. And I'm totally with you. Thanks for doing that, because I also strongly believe we are actually in a pretty good place at the moment. There are always things that we can improve, and I think we had some interesting talks these 2 days of where we can improve, but we are starting from a pretty high bar already. Also, thanks for the Douglas Adams reference. That's always a good one. Before going through my list of questions that I wrote down during your talk, we already have one in our virtual conference venue in the Mattermost chat from Daniel Thomas. Daniel, do you want to ask yourself, or shall I read?
I can ask it.
Please go ahead.
So will IoT security only come when the number of providers has consolidated to a relatively small number, like with mobile devices, or say with big tech companies, you basically have to go with one of a small number, and therefore they have the reason to invest in security because things have settled down a bit? And if that is the case, is there any reason it wouldn't happen with IoT? I don't know, because of the being so many different application domains, or do you expect that everything will consolidate behind a small number and then we'll get security?
Sure. So that's an interesting question. Thanks. So I think the two kind of the number of providers and the level of security, kind of thinking about it off the top of my head, I think there's probably some correlation there, but not necessarily causation, right? Like I think the two may be driven by the same market forces, right? As early on in the field, there are lots of entrants, lots of people trying different things. As the field becomes mature, it kind of tends to consolidate to a few big players. And it so happens that kind of security evolves along, that same curve as well. And I think actually the kind of the slide I had in backup that I accidentally showed talks a little bit about that point. Maybe I'll go to it, right? Let me just do that. Well, so speaking of IoT, right? Like, look, these two printers, a few weeks ago when I checked this, right, they think they offer pretty much the same set of features. They have the same price. How can you tell which one is more secure, or like is even secure, right? And maybe this is a counterexample to what I was saying before, that once a product category becomes commoditized, that's when it focuses on security, because these things are commoditized, right? Like I think people go to the store and they just figure out, okay, like, I want a printer that costs like this much, or, whatever the cheapest, whatever is in store at Costco, and you just buy that printer. Right? There's not really a lot of, I think, feature differentiation for home printers these days. But then the question is, to what extent do consumers care, right? Like, how many of us have like our work, have a problem with the security of our printer, like can't get our work done because our printer, is being exploited, right? So, you could argue that, look, they reached a level of security that consumers are comfortable with. And, if you made them 10 times more secure, like nobody would notice, right? So, yeah, so I don't know, this was kind of a long-winded answer. I'm not sure I answered the question directly, but I think we will see, I guess, that consolidation and improvement on security that are kind of, they'll go hand in hand, but it's not because one is related to the other. I think you can have many different vendors all improving security, but you do have to wait for the product category to mature. You have to figure out what customers are actually comfortable with, what benefit they're really looking to extract from a product, and what trade-offs they're willing to make in exchange for that. Right? And you don't know that until you try, right? Like, look, I can look at Uber, right? Like something like Uber would have been insane to propose like at any large corporation before Uber actually launched, right? Like, look, we're gonna, can you imagine that conversation with the legal team? Like, we're gonna let strangers like get into your car, and it doesn't happen, right? So you have to go kind of through this evolutionary process to see what sticks, what works, what consumers embrace, and then kind of work on securing that. Anyway,
coming back to your answer, at which point in your curve would you, in your time curve, would you put current mobile phones? Do you think we are already at the stage where the differentiating factor is becoming to be reliability? Or
yeah,
how far away from that are we?
No, I think for phones, my personal take is, look, and it's not a great thing kind of from a business perspective for the industry, but I think we've kind of turned that corner effectively, right? Like, all phones look like this, right? You don't really see lines forming around the block whenever the new, the latest phone comes out. People are not treating their, their 2-year contract as a prison sentence, counting down the days to when they can finally get a new phone. At least, like, look, for myself, right? It's like, it works well. I'm not necessarily looking forward to an upgrade. I know that, for me, really the last few generations of phones, like the upgrade was driven by, battery life, the battery degrading and screens getting broken, right? It wasn't because the new phone offered the features that I wanted. It's because my old one stopped working. So in that sense, like, yes, reliability is already a thing. And yeah, like at this point, I do view getting a new phone as a chore, right? Like, okay, now I have to migrate all of my stuff and reset it up. And again, not a great thing for somebody kind of whose salary depends on people buying new phones. But from a security engineering perspective, I do think we turned that corner, and that is why you see, like, I'm not naming names, but you see the big kind of players in the industry kind of made a rather sharp pivot towards kind of strong focus on security.
Coming quickly back to your example on printers, I fully agree that phones are becoming commodity devices these days, and there's a little difference in terms of features. But do you think that for phones, we already have like, as consumers, trying to put ourselves into consumers' shoes, do we already have the information? Do we have the transparency on how to decide between the security features, the security stands of multiple phones that you have in your short list of devices that you might go for? For printers, I agree. I wouldn't know where to look for if I wanted to know if it was safe to connect that printer directly to my whatever guest network or not. Do I know for phones if I'm not within this community here?
No, and I think that's the same answer, right? Like, unfortunately, no, right? And we don't have a good way. And like I said, I think part of it is because we don't really have this meaningful feedback function. We don't have reliable crime stats. What you really want to know is, okay, what is my likelihood of being exploited or losing money or whatever it is, right? If I buy this phone, right? I think we try to short circuit that and look at features, but I think it doesn't necessarily work, right? So, the worry is that like, it's possible to slap on a feature without actually making the device more secure, right? Like, look, I can, if I buy a cheap phone that's based on an SoC that's not from Qualcomm, let's say, right, and I slap a secure element to the side of it, it doesn't magically make it secure, right? It doesn't like address the hundreds of kind of LP and RCE bugs that are in there like that. So kind of adding a security feature by itself, right, just like adding a safety feature to a card doesn't necessarily mean that you get the outcome that you want. We have to get to the point where we're actually able to measure outcomes and look back and say, okay, look, clearly, people that have bought this type of device ended up being safer than people that bought that type of device.
We do have another question in our Q&A session chat. You said, by Martin, by the way, you said we are past arguing if some bug is really going to be exploited or not. What do you think is the next argument that we should move past?
All right, so I guess I'm going to be, I'm going to keep beating that same drum. I think it's, I think we spend too much time arguing about whether something is a good idea, right? Like whether a certain mitigation really works or not, whether, kind of, I'm thinking of, hover flakes kind of mitigator and or kind of spenders kind of opinions on kind of what mitigations really work in Linux and so on. I think, I mean, they're interesting intellectual arguments, they're interesting academic arguments, but really we have to rely more on kind of on the evolutionary and the scientific process, right? You don't make progress just by kind of thinking really hard about what's a good idea and then stopping there, right? You have to then test it out and see if your hypothesis was correct, right? So again, we need this feedback mechanism that will allow us to try lots of different things and not get hung up about kind of philosophical or maybe arguments about whether a certain mitigation is good or bad. We should be able to look at the data and see whether that mitigation is working or not, right? Whether it's actually making users safer or not.
I have another one, which is very much connected to your take on reliability being one of the latest features that products aim for. Do you think that this curve will go down again? If I look at some product categories, again, let's not talk too much about smartphones because both of us would have to talk to some lawyers maybe. But if I think about whatever, washing machines, to take another example, it probably also works for cars. I feel that reliability is actually going down over the decades, that maybe it was an argument that your washing machine would run for 20 years. It no longer is one.
Yeah.
At the moment, we are back into the feature cycle. Hey, this washing machine speaks IPv6. Isn't that cool in itself? Wouldn't you want it because of that? So do you think that this is a curve that saturates at some point, or based on the product category and based on whatever the current market hype is, can it actually regress back down again? Is that something that you would expect also in the mobile and IoT space to happen, to have a little bit of back and forth?
Yeah, absolutely. I mean, I think reliability regresses. I'm not sure about security, but I mean, I don't necessarily see kind of in terms of that curve. I think it's just basically, it's a second wave, so to speak, right? You know, using the terminology of today, you get a second wave, you get a third wave. In fact, I mean, we already saw something like this with phones, right? Like with battery life, right? Like, you know, the phone that I showed from 95, right? You know, back then, like we had a week of battery life, right? That was, you know, you want to be able to go for a week between charges, right? Like now we're lucky if we can last a day, right? And that's because obviously, you know, you have this kind of huge color display and a lot of other things, right? And a much more powerful processor. So you have certain kind of reliability things that are, they degrade because consumers embrace new functionality, new features. Yeah, so for washing machines, somebody really wants kind of is buying a new washing machine for kind of for Wi-Fi connectivity, and they're willing to kind of to trade longevity for it, then that's what happens. But again, right, we, you know, largely these are the choices we make as consumers, right? It's like in most cases, like you don't have to buy the Wi-Fi machine, right? Like we didn't have to use Zoom. We could have tried something more secure, but then it would probably, you know, I'd probably need more than 15 minutes for the AV check. I don't know. Hello? Can you guys hear me?
Yes.
Oh, look, Renee looks frozen. Oh, there he is. Oh, still on mute. There are two Renees. I see one video talking, but the other one is muted. Can anybody else hear Renee?
No.
Renee, I think you're muted.
Okay, sorry about that. So now I had a glitch. The Zoom client actually crashed on me, and upon restart, of course, decided to use a different audio device. Yes, Alex, I do fully share your concerns about the Zoom client. And as you so acutely mentioned at the start of your presentation, there are reasons why we chose it. Not only because our university actually has a campus license for that, which allows us to use all those features without paying from the conference budget, which we don't have. So yes, there are reasons. If we don't see any other questions right now, then I would like to close this excellent keynote session. Thank you again, Alex, for doing that. It was very much appreciated. And we go into a break for a bit over 10 minutes, and we'll then continue with the closing keynote by Sudhi Hurl from Google. Thank you, Alex.
Thanks, everyone.
Have a great day back in San Diego.
Okay. Thank you, everyone.
Welcome again, this time to our last session of the Android Security Symposium and the closing keynote, which will be given by Sudhi Hurl from Google, who has taken over the Android platform security team and has done a wonderful job with the security features of Android 11, some of which are can already be seen in the current beta. Sudhi, I wish you a very good morning to the West Coast as well, and over to you in Mountain View.
Hello, everyone. Good evening, good morning, as the case may be where you are. My name is Sudhi Hurl. I lead Android platform security, as Renee was mentioning. Today I will be speaking about icebergs in Android security privacy, trying to understand information asymmetry that exists in the platform and our users. I was really looking forward to being in Austria for this particular symposium and sharing a Radler with Renee, but unfortunately the COVID situation has made things very difficult for all of us. I hope you and your loved ones are safe and healthy. With that, let me get started into talking about my favorite topic here. Iceberg number one, preloaded applications. As you may know, there is a lot of media hype, media concern around security and privacy risk coming from pre-installed software. In point of fact, Privacy International sent a note to our CEO, Sundar, asking Google to take action against these exploitative pre-installed software on Android devices.
Sudhi, sorry for interrupting. We can't see your screen share yet.
Oh, you cannot?
At the moment, you cannot.
Can you see it now?
We see a screen share, but within the screen share, I see you at the moment. Perfect.
Can you see the second one now?
Yes, perfect.
Sorry. As I was saying, Privacy International sent a note to Google, Sundar Pichai, asking Google to take action against these preloaded exploitative software. So, the question to ask right now is, what really is these preloaded application and why is it so bad? Well, every Android device ships with a lot of preloaded applications. They fall into broadly 5 categories. Mostly from the OEM, i.e. the phone manufacturer. We call them first-party applications. Some preloaded applications are from system-on-chip vendors. And oftentimes, they have the power to act on behalf of the Android platform, i.e. they enjoy very high privileges. The third category is a set of Google mobile service applications, which almost every OEM includes required by contract. This includes Google Play, access to the Play Store, Gmail, etc. And then there are carrier applications required by telcos. Typically, you need them for provisioning new accounts, voice over LTE, customer support, etc. And finally, the last category is third-party applications, which are none of the above, but are still preloaded on a mobile device. Many of these are risky due to the permissions they have. They're not, preloads generally aren't inherently bad. What makes them bad is the fact that the elevated privileges causes bad things to happen for the user. How do the OEMs preload these software? Well, they don't just bundle the APK. Some OEMs don't know what happens when something is signed with the platform key. And so, they sign these applications with the platform key, and now suddenly these third-party application, which was not written by the OEM, now has the power to act on behalf of the platform. In other cases, these preloaded applications have been pre-granted extremely large permission and privilege surface. Let's take a look at some real world numbers. So if you look at Android 10 API level 29 and see across a variety of OEMs, what does the number of platforms and applications look like? For baseline, I'm looking at GSI, which is the Google System Image, which is the absolute bare minimum version of Android, i.e. AOSP plus Google mobile software that's required to run a phone. When you compare it against that, it has 53 platforms and applications. But across the ecosystem, almost every OEM that we benchmarked has vastly more platforms and applications. Well, I just now said that preloads aren't necessarily bad. What makes them bad is elevated privileges. So I'm going to double click a little bit on just one particular permission, install packages. And if you again look at the AOSP baseline and what's in GSI, we only have 3 packages there with the install package permission. But when you look at it across the ecosystem, some of the very large outliers include anywhere from 25 to 30 different applications that can install packages on behalf of the user. So we think this is problematic because users often don't know that these preloaded applications have these permissions, and therefore they are unable to make sense of what their device can or cannot do on their behalf. Well, the next question is, what can we do to improve the status quo? I think Rene, in his introductory keynote, shared some plans. We totally support that. We encourage the university and the research community to build a consumer accessible transparency database to catalog these preloads and build a risk score chart across many devices and OEMs. This is especially important for consumers because information asymmetry. While we in the research community are fairly well versed in understanding what consent dialogues mean, what a VPN or a proxy means, and what certain permissions mean, the average consumer, by and large, has absolutely no idea. And so it falls to us, the research community, to raise the consumer awareness to this problem and provide a guided path for consumers to make safe purchase choices. As an analogy, when I go to buy tires for my car, depending on what type of car I have and what my road conditions are where I drive every day and what my skill level is, I can pretty much choose a very precise tire that is Z-rated, that has this kind of tread depth and this kind of grip and stopping power, etc. So regardless of whether you're a sophisticated car driver or not, there is a guided path for consumers to make the right purchase choice for their car tires. Now, analogously, we don't have that in Android. If a consumer wanted to make a purchase choice for an Android device based on their security or privacy stance, there is no guide that tells them what they should be looking for. And I'm really hoping that the research community and the consortium that Rene is trying to build will step up and provide this lighted path for consumers, and in some sense, close the information asymmetry that exists today. Iceberg number 2, firmware complexity. Well, here is a block diagram of a phone from a few years ago. If it's not very clear, I apologize. It's a very low resolution picture. We commonly think that a phone has one CPU, which runs Android. Many of you know that there is also a modem CPU. But what most of us seem to, in the back of our mind, we know, but we tend to ignore it, is that there are other things that also have quote unquote CPU in them. Your Bluetooth Wi-Fi controller, your GPS controller, your LCD controller, your USB controller, your DSPs that is used for modem, your camera ISP, all of these are little CPUs. Yes, there are CPUs everywhere on a modern phone. It's not just the ones that you commonly know, but there are lots and lots and lots of them. And they all run some kind of embedded software, typically called firmware. And almost always they are distributed as binary blobs by the manufacturer of that particular component. The The interesting thing to ask here is, do we know what's in each of these blobs? Are they regularly updated with security fixes? Do they really come from the OEM or the chip vendor? Did anyone else interfere with them in the long supply chain from silicon vendor to OEM factory to end user? And also, you know, from a security practitioner point of view, it's interesting to ask, are these images signed? Does those little tiny CPUs use verified boot to check the signature of each of these firmware blobs? What does this mean to the average consumer? Well, from the consumer point of view, it's useful to ask, did the system software on their phone really come from the manufacturer? Is the system software on their phone the same as the one checked by Google? Did the OTA update that they just received, was it broadly distributed to every user, or was it more narrowly built and targeted to some subset of users? These sorts of questions are really, really difficult to answer today. And this opacity that exists at the lower level is something that, you know, I'd like to call an iceberg and requires more attention from the research community to fix, you know, what I call another information asymmetry here. The practitioners and the manufacturer of the devices have vastly more information than the consumer, whereas the consumer feels the impact of some of these decisions that we collectively, the community, make on their behalf. Finally, I get to my last iceberg, which is security UX. We all recognize that credentials are our most valuable digital asset. We use our credentials everywhere today, from ordering food to groceries, banking, investment, and in many countries, your access to government services is also done digitally. So safeguarding your credentials becomes the most important thing, right? Well, security non-experts have always maintained that you must use antivirus software, strong passwords, change passwords frequently. Well, all of you have probably worked in at least one company where you had an IT policy that says you must change your password every X number of weeks. Whereas when you look at security experts, what they recommend as safe online practice, it comes to very boring stuff. Install software updates regularly. Choose unique passwords for each service that you use. Oh, and for the love of everything that is nice and holy, please use two-factor authentication. And use strong passwords and use a password manager. Don't write things down, right? So we as practitioners, we follow these sorts of guidelines. But every now and then, we log into our favorite service from a different computer. And then the system throws up all kinds of alerts and safeguards and says, prove to me who you are, right? While some services do a very good job of identifying users coming from a potentially different place than what the system thinks the user should be coming from, it's not always obvious. Even some of us who are very sophisticated sometimes receive an email that says my billing, that there is some difficulty with billing. Would you please click here and update? Right? Imagine getting this email while you're watching the show and you got up to get a drink or a glass of water or whatever. You check your phone and here is this email. Well, how many of us actually take a pause, go back to our desktop, open this email, look at the URL and say, aha, this is a phishing email. I must not click, right? Our first instinct is to look at this. Well, it looks like Netflix. Well, it kind of looks like the Netflix red button. And it says your friends at Netflix. So it must be true. Let me click on it. Right? My point is that stressed humans are cognitively impaired. And these stresses and stressors occur in our day-to-day life when we're doing a lot of, when we're using our mobile phones in everyday scenarios. And information asymmetry does not help this situation. If you're not an expert or a security expert, it is really difficult to counter some of these attacks that have become really, really sophisticated in modern times. I guess the answer to this is for us to pay attention to the user experience when we throw up security alerts or caution dialogues or change the workflow because of a suspected security incident, we need to make sure that we think about the information asymmetry between the practitioner and the user on the other side. I want to close with an example of what happens when you close information asymmetry gaps. In 2007, there was a research article in the Quarterly Journal of Economics where the author explores information asymmetry that existed in the fisheries segment in the state of Kerala, India. So prior to the introduction of mobile phones, I'm talking mobile phones, not smartphones. So this is 2007, the year that the first iPhone was introduced. And in India at that time, the feature phones were still pretty common. And so before the introduction of these mobile phones, there was tremendous price variability in the spot price of fishes in different regions within a single state in India. And the chart on the left shows you the gradual ramp up of mobile phones. The moment the penetration achieved close to 100%, you can see correspondingly the price variability also dramatically dropped, right? In hindsight, this seems obvious, but to me, this is remarkable example of how closing information asymmetry gaps leads to beneficial effects for our consumer. When we think about security and privacy, it's not just an algorithmic process or a cryptography or a legal policy compliance, etc. We absolutely must seriously consider the human angle of it as well. So there is need in the research community to focus on the humanist side of security and privacy. We must think holistically about security and not just get stuck in the weeds. And we should always pay attention to the consumers. Thank you. And if you have questions, I'm happy to answer them. Otherwise, I hope to give back some time. We seem to have ended at 9 a.m. Precisely on time. Thank you.
Thanks a lot. Thank you so much, Suri, for that closing. I am watching our chat for questions right now. Right. If anybody has questions, just please also use the raise hand feature in Zoom, or just simply unmute yourself here. So I will, while people are still typing, you mirrored something that Alex has said in his keynote before, the issue of complexity. One of your icebergs that I'm fully on board with is complexity, and how specifically for modern phones, this seems to be exploding and actually getting worse year over year, both for hardware and software, be that firmware or what we typically call the system software. Where do you see this going? So how do you think we can manage to cope with this complexity? Or would you say that we just have to deal with rising complexity and mitigate, make small pockets of lower complexity and deal with those instead? What do you think? Where are we heading, or maybe where should we be heading?
So my fear is that the security community is not uniformly distributed across different micro segments within our field. For example, one might say that people who make merchant silicon system on chips and folks like Google Android team, we may have excellent security engineers, but the same possibly cannot be said of smaller players that make LCDs, LCD controllers, or smaller companies that make a dedicated chip for doing some particular task. And the reason why I think I'm mostly right is these smaller players show up in the IoT segment very, very frequently. And if you want to see where the broader information gap exists, all you have to do is look at the IoT segment and see how many of them practice safe security practices? There was an article in ZDNet that I read a couple of days ago that said majority of consumer routers worldwide never receive security updates. Right? For us, this is mind-blowing because we think that this is a solved problem. We have tools, we have well-known techniques for doing Delta-based software updates, right? You have orchestration systems, multiple open source orchestration systems for doing over-the-air firmware update, yet nobody does this, right? If we dig deeper, I suspect we will also discover that as you go lower into the firmware stack, basic things like secure verified boot may also be missing, right? So the answer may be that we need to educate the next generation of students and researchers and practitioners to think about security from the ground up and know what are these constructs and make sure there is an opinionated path for some of these security constructs. When Google discovered that TLS SSL is a foundational element for the web, and OpenSSL would have every alternate Tuesday with a new bug report, somebody at Google called Adam Langley decided that security needs to be boring. They created a boring version of OpenSSL and called it Boring SSL. I'm wondering if a similar boring security approach needs to be taken for a variety of narrowly scoped components across our technology stack, right? Eliminate the complexity associated with choice and provide narrowly scoped answers to common problems. Maybe that's a good starting point.
Thank you. We have a first question by Daniel, who is also, I think, still dialed into the meeting. Daniel, do you want to ask yourself?
Okay, so you talked about credential stealing and basically phishing on mobile, which is, I think, worse than on desktop, mostly because there's not enough screen real estate to show as much detail. So how do we address phishing on mobile?
That's a very good question. I don't have answers, but my intuition is that we need to do much more user studies, UX experiments to see what is the best way to surface this. It's not entirely obvious to me what is the right answer here. The reason I raise these problems is because I don't have answers. I'm really hoping that the research community can invest a little bit of time thinking about the user experience of security issues and come up with hypotheses and test them. Renee, do you have a better answer than this?
I agree with Daniel that probably for mobile devices, the hard part is real screen estate, which maps back to what you also said in your talk, that attention is one of the key elements. How do we manage attention for users who are attention overloaded, who are stressed? Maybe the answer goes back to what you said in reducing stressing factors, stressors, to be able to allow to concentrate on the right things. But again, I don't have a good answer because that question on how to surface the right amount of information on a very small screen, I think has existed since we had devices with small screens, since we had first smartphones. Unfortunately, I don't have a good answer to that either, besides trying out different things, trying out how we can surface the right amount of information, which incidentally actually maps to the second question that we had pretty much at the same time in the Q&A chat by Paul Blundell, who I don't see dialed into the Zoom meeting, so I'll just read it. Do you feel the Android permission system is a success? If you could step back 10 years, what would you do from the start differently? I love that question because hindsight is such a good thing, specifically in security. So Sudhi, what's your take?
This is an excellent opportunity for me to put my foot in my mouth. This is a very, very good question. You know, in hindsight, I wish we were a little more diligent in thinking about all sorts of permissions, their interactions, and how do you determine which of these permissions require user consent versus not? And how do you surface these consents to the user? I wish there was a little bit more understanding back then. I'm not saying people didn't think about it. Because Android was so new, because smartphones were so new, the available information space for you to wander in was obviously very limited, right? But if in the future we have a chance to do so, I think a good way to look at it is to partition permissions into those that are sensitive, and which of these require user consent, strong user consent, which of these deal with private data, right? Figure out a few of the axes that are important and try to put each of the permissions in some hypercube, n-dimensional hypercube, so we can reason better about them. Right? Today, they're all in a flat space, and it makes reasoning very difficult. And because of backwards compatibility reasons, we are forced on an incremental approach of solving the problem. Maybe it'd be interesting to see if somebody in the research community totally rethinks the whole permissions thing without worrying about backwards compatibility or forward compatibility, and reimagine what is the right way to present this information and build a prototype. Might be very interesting to see what we learn from that exercise.
Yeah, I can think of one particular example where many of us are probably now eating our words, or feeling that had we known about the current situation, we would have decided at least that one tiny thing of permissions grouping differently, which is the BLE beacon scanning permission in the location group, right? With all the exposure notification apps, the contact tracing apps out there, that has become a major hurdle to adoption, that they have to ask for the location permission group for very good reasons. Historically, there were good reasons why this was put in that group, but right now it's the wrong grouping. And so, yeah, I totally agree. I think those will have to change and will have to be redefined as we go on.
Yeah. And I really think the research community has an opportunity here to reimagine the world and present some results, good or bad, of how this could be rethought, right?
Mm-hmm. We have another question in the chat from Martin. Is reducing information asymmetry something that drives the design of security controls in Android?
Yes, I think so. I think a large part of our day-to-day conversations is around how do we make the user really understand the choice presented to them, and is the choice comprehensible to the average user, not one living in Bay Area building Android devices, but really one of our 2.5 billion users worldwide. Can they really understand when they say allow for a particular permission? Do they understand what that means? And we also spend a lot of time thinking about information asymmetry that exists between application developers and the platform developers. And how do you make sure that certain APIs cannot be abused or misused, right? Either intentionally or accidentally, more often than not accidentally. And so we spend a lot of time thinking about what a particular feature means to its constituent, be it the developer or the consumer. I don't know if I answered that question, but yes.
I think so. I'm just double checking the chat to see if we have any other questions. I think people are still typing. So as we are nearing the end of this symposium, I guess this is a case of last call for questions. We can, of course, also take them offline. So that's something that I'd like to encourage all participants to still use the virtual conference venue even after we close the live stream, because this dedicated chat system instance will remain open. And feel free to just keep using it for at least a week or so to either interact, to connect with each other, or to just continue asking questions in the program day 1 or program day 2 Q&A session chats. And authors can then maybe just answer those questions also in textual form. Otherwise, Sudi, thank you so much for doing this. Thank you so much for closing our Android Security Symposium with this talk. I'm also pretty sad that we couldn't have you over here in Linz. Even the weather has turned out nice, very nice today. But the promise still stands. We will have proper food, proper drinks over here in Austria. I'm certain that there will be other chances to do so. And of course, we're all hoping for the travel situation to clear up somewhat.
Yes, indeed.
When that happens, nobody knows. But I'm optimistic, I'm positive it will happen, and then we will get you over here to Austria and show you the sites. That's a promise that still stands.
Excellent. Thank you so much. I look forward to it. And thank you for having me, Rene.
Yeah. Thank you, Sudi.
Thank you for everyone for helping me with everybody in the JKU staff who helped put together the symposium. And
yeah. Thanks, Sudi. I wish you a great day back at the West Coast. And I'm handing over to Michael Roland for our official closing words for this year's symposium.
Thank you.
Yeah, with this, I would like to thank you all again for this wonderful symposium. And also, I want to mention that all of this wouldn't have been possible to manage if we didn't have all our staff in here. And for that, I would like to hand over to my staff to show you all who the people in the back end are and who helped make this all work so great.